PowerPoint, so that's a massive benefit.
Oh yeah.
Right, I've just started streaming. You should see the intro slide if you watch. I don't think Viper's going to come along. If he does, he can just join in, 'cause I think we better just kick off. So if you can make sure you can see my screen without any issues, and with that we'll crack on.
Yep, we can see
I
it.
can see it very well.
Okay, good. Okay, so we're going to cover quite a lot today. The first half is sort of the concepts that you have to know and understand, to go on to the later part where we actually look at navigation and how we plan a flight and how we actually execute that flight. So there's a lot to go through. I'll try to keep it at the right level. If you want to know more, please just let me know. If it's not seeming relevant, also let me know. Okay, this is the first time I've ran through this, so there probably is stuff in here that's maybe over and above what's required, but we'll need to tailor it once we've run this session for future use. We'll have some breaks. I reckon it'll be between 1 and 2 hours, but we'll break it up just so everybody can kind of get a chance to chill out and digest what's been said. We'll take a couple of 15-minute breaks here and there if needs be. Please shout out any questions as they come into your head. Don't wait, just interrupt me, because there might be something that I've glossed over that's crucial to your understanding, so I'm more than happy to take questions as we go. And also, if it's boring you, just tell me. If particular topics aren't what you're interested in, let me know. Some of it's quite technical. Some of it's maybe not as relevant to flight sim, but an understanding of it's still important. So as you can see, we're going to go through methods of navigating, different ways of doing it, the principles of dead reckoning, the difference between headings and tracks, the difference between magnetic and true courses and headings. We're going to look at wind components, so we're going to break the wind down and see how it affects the aircraft and its path. We're going to look at air speeds and ground speeds. We're then going to look at combining all of what we've just talked about, and compensating for the wind. We're going to briefly discuss the importance of fuel and time management, and then we're going to run through planning a flight, and then also actually flying using dead reckoning, so techniques that you might need to use as you fly, how you actually use the information that you've produced in your flight plan, and then correcting for any errors in that sort of navigation plan that you've produced. So there's some bits in there that are a wee bit more than what's shown on the screen, but that's it at a high level. Is there any questions or requests before we move on?
None, but this is amazing and I'm very excited.
Right, okay, good. So, what is the point of navigation? According to Wikipedia, process of monitoring and controlling the movement of a craft from one place to another. That's very formal, and quite pompous. The purpose is navigating from A to B, and as pilots, that also includes avoiding obstacles, terrain, and weather, and probably more importantly, in some instances, accounting for airspace. If you look at a sectional chart, there's airspace all over the place. There's airspace on top of each other, but yet you can't actually see it when you're flying. So it's really important to know your position in order to avoid busting airspace, as we call it, which will get you in trouble. If you enter airspace that you're not supposed to be in without a clearance, you'll get in trouble. So that's a massive part of this. We also have to give consideration to the aircraft performance and endurance when we're navigating, and we'll come on to that in a wee bit. So there's loads of different ways you can navigate. You can do it using navigational aids, radio beacons, and the picture in the background here is a sort of typical, maybe late 90s IFR panel, just before we start to move into GPSs, and you can see a couple of GPS units there. Okay, now that is a separate sort of form of navigation, but very closely related to radio navigation. And that, in a lot of instances, actually superseded radio nav. You can also then navigate by unconventional means, which is essentially knowing the area and just looking out the window. And that's a perfectly valid way of navigating. But if you are somewhere unfamiliar, or it's important that you follow a specific path, there's a thing called dead reckoning. And dead reckoning is a very old way of navigating. It's carried over from ships, but it's still a really good, useful task. Dead reckoning on its own is rarely used as navigation, the sole means of navigation, but understanding the principles of dead reckoning and being able to apply them will massively help in other forms of navigation, including radio nav and GPS based navigation. Tarek, probably one for you. There's a term in America, pilotage, that they use. Is that synonymous with dead reckoning?
I
'Cause-
believe it's almost the same, and if Null knows the difference, he could correct me. But um, the difference is when we use dead reckoning in Europe, it's a slightly different way of doing it. So in Europe, we use it mostly using calculations and stuff, whereas in the US, it's just a shorter version of dead reckoning. So you do point by point, so kind of pinballing between visual references. I don't know if that's the term pilotage, but honestly, it's a good question that I don't know the answer to.
Yeah, I mean,
Yeah.
I remember seeing a Flight Chops video and he was doing some pilotage in the Stearman, and it was very much seemed to be feature crawling, as we'd call it. It was just a point for Null. If you're getting into flight training, you'll probably be getting taught pilotage, but as Tarek says, likely very similar.
The only time I think I've ever heard that a friend of mine's father was a naval aviator, and it was in reference to bouncing between land and sea, I guess sea marks, right? Like, specific areas where like a coastline would meet.
Yep,
And then it had the ring of like when you're taxiing and do procedural taxiing where it's like just only one step, like only go here, and then you're not thinking about anything else. So maybe.
right, okay. So this is probably a slightly more advanced but similar technique that we're going to look at today, dead
Aye.
reckoning.
I just confirmed it. Pilotage is feature crawling,
Okay.
and which is highly disregarded in the UK, but in the rest of the world it's fine because it's a fantastic way to navigate. But anyways,
Yeah. So, what is dead reckoning? Once again, shamelessly stole this textbook definition from Wikipedia. The process of calculating current position of some moving object by using a previously determined position. So what does that mean in real terms? So we define turning points on a chart. We plot track lines between these 2 points, and we will measure the distance, calculate the time that it will take, and then we will also calculate a heading to fly based on winds. That's it, really, in a nutshell. In flight, you estimate your actual position at regular intervals, and you compare your actual position, or your estimated position, to your planned position. So where am I? Where should I be? And you correct your heading to compensate if needs be. Okay. Now, as much as I'm saying this is a very old technique, um, modern airliners use an inertial reference system. Martian, there's loads of tidbits in here about sort of modern airlines and or modern systems and how they work. So you'll be glad for that with your aeronautical engineering background.
Yeah, sure.
So they use a thing in modern aircraft, an inertial reference system, which spawned from an older system called an inertial navigation system, which basically, in short, you supply it a starting position. You give it a north and a west position, or a south and an east position, essentially a coordinate, and then using gyroscopes, it tracks every change in heading, every movement the aircraft makes to calculate its new position. And using that, you can very, very accurately maintain a reference of where the aircraft is in space. Okay. It goes by lots of different names now. Airbus seems to add a new letter to the IRS every year. They now use laser gyros. They now have GPS feeds into them to maintain the position even more accurately. But at the end of the day, it's using the principle of dead reckoning. You feed it a start position and then it tracks all your movements
Aye,
to compute your new position.
the term with Airbus is GPIRS because it's a combination of everything.
There you go.
Just to make things easier.
So we are going to be looking at this chart here on the left. We're actually going to follow through and plan this flight. When I initially came up with this sort of proposal, considered doing the theory and then actually going and flying it. It's probably going to be a bit too much given what the theory's turned into. But in the next session, it's a good idea to actually do some navigation, have you guys plan flights and follow them.
That sounds great.
Yes.
And we can actually apply it, which is always the fun bit. So what we do is we plot the flight, and you can see here, this one that you can see, you're going to see a lot of this. This is an actual flight that I flew. I just so happened to still have it marked up on my chart, so I thought I'll just use that. I scanned it in, and turned out it came out quite nice, so we can actually all use it together. But what we do with those tracks is we transfer them into something called a plog or a pilot log. And this is the thing that you really use in flight. This is where you record all your calculations, the headings that you're going to fly, distance, the time, and that's how you work it. And the chart's there for reference. So the chart's sort of used in conjunction with the plog, but once you're in the aircraft, the plog becomes the main focal point. Okay, we calculate ground speeds, distances, estimated time en route, heading to steer, all based on predicted winds. That's a massive thing, and we'll come on and I'll let you guys have a go at that. I've got a nice flight computer simulator that I can let you loose on, that you can do some calcs for me. Okay, and as I say, that's what we use to monitor the flight as we progress. Any questions on what dead reckoning is and how we do it so far?
Nope. Very clear.
Good. 5-second rule. So we'll come on to actually doing this plotting and flying a flight using dead reckoning, but first we're just going to cover some basic concepts, okay? So I've already used two terms that you maybe aren't familiar of the exact differences of, and we covered it in the crosswind lesson last week. So it's heading versus track. So what are the difference, or what is the difference between these two terms? So the heading is the direction in which the nose of the aeroplane is pointing. Simple as that. That's what your heading is. There's some different types of headings, and I'll cover that in a second. But that is the direction of the aircraft, the direction that the aircraft is pointing. The direction that the aeroplane is actually travelling across the ground is the track. Think of it as a train track, if you want. Heading and track aren't always the same though, and that's an important thing to understand. And as you can guess by this diagram on the right hand side, that's technically correct but horribly complex, the wind has a massive factor on that. Okay, so track is equivalent to the compass bearing which you would follow if you were to move from A to B across the ground. In a nil wind situation, then the heading would be equal to the track. But whenever you have any kind of wind in real life, that's pretty much always the case, especially altitude. Your heading will be different from your track. Difference between these two things is known as a drift angle. Okay. And I'm just introducing the terms that I've underlined here. These are things that you that we'll start to use throughout the presentation. So that's why I'm trying to introduce them and explain them early. Okay. Again, in real life, due to winds aloft, the heading and track are different. Is that clear? I think Martian, Null and I had discussed heading and track when we'd done the crosswind, just because I was working with Null and he was asking. Are you familiar with these terms already?
Yeah, this is all good. Thanks.
Okay, good. So let's take an example. We're flying between two towns. We get the protractor out, we put it on the chart, and we measure that the track between these two towns is 090. Okay, so we take off and we point the aircraft at 090, and as luck would have it, we've got no wind. For some strange reason, we have no wind. So by pure chance, we will track 090. So that, in this case, heading and track are the same. Now let's say we take off and we go to do the same flight the next day, and we point the aircraft heading 090 again. But this time we've got winds. What's going to happen, do you think?
You're going to be pushed to the north, right? Like, so you'll be your track will deviate to the north.
Martian, would you agree with that?
Yeah.
Exactly right. So you would end up tracking north or towards the north as opposed to flying a track of 090. And that's not ideal for a number of reasons. If it's a short leg, maybe it doesn't matter. Over a longer leg, you're gonna struggle to get to where you want to go. So it's important to account for that wind. So how could we, with this wind, track 090?
Point a few degrees to the south.
Correct. We would point into the wind. In this case, I actually calculated this, and it's a very minor difference because the wind's only 5 knots. But even a 5 knot wind, because it's a pure crosswind in this instance, causes a heading requirement of 093 to track 090. Okay, so that's it. You're pointing into the wind to compensate for the crosswind. And we'll look at that in a bit more detail. So if you understand that concept, you're going to do well doing some navigation, because that's all you're really doing with navigation. You're compensating for the wind, and the trick is how much to compensate by. So if that's clear, nobody's got any questions. The next thing I want to briefly cover is the difference between magnetic and true course, or magnetic and true heading. Does anybody know? And if not, can anybody take a guess at what these two things are?
Well, the magnetic pole is not on the North Pole. So magnetic would be pointing to the magnetic pole, true to the true pole.
Absolutely spot on. Compasses work by sensing the Earth's magnetic field. They actually sense any magnetic field. In their simplest form, it's a magnet floating in water or oil. But they are designed such that they're really trying to sense the Earth's magnetic field. So the heading shown in the compass is relative to magnetic north, not true north. And the difference between magnetic north and true north can vary quite significantly depending on where you are in the world. So the difference between these two is known as variation. Now, why does this matter? Why is it important? Well, charts are all plotted with reference to true north because magnetic north doesn't vary linearly across the world. It's kind of all over the place. So if you try to plot your chart based on magnetic north, it would be a mess. So it's plotted with reference to true north, but that then means that when you are measuring out your tracks on your chart and trying to calculate your headings to follow, if you don't convert those to magnetic headings, you're going to be pointing the wrong way, or you're going to be off with your heading, and you're going to get blown off track. Okay, so it's really important to understand the difference between the two of them in order to understand when you apply it and which one you need to use. On the chart, there's isogonal lines, and they show what the variation is in a given area to allow conversion between the true and magnetic bearings. And likewise, very rarely done nowadays, but if you were plot and your track made good, you would have to convert your compass heading to a true heading. So you'd need to go the other way in order to plot your track on the chart. Okay. For this reason, it's very important to keep electronics or magnetic items away from the compass in flight. Your flight instructor will wrap your knuckles with his ruler if you put your headset up on the glare shield after you finish flying or before you finish flying, because it can actually cause issues with the compass. It's a very sensitive magnet. It has to be in order to sense the magnetic field of the Earth, which is relatively weak. So if you're flying using the compass, or anything synchronized to the compass for that matter, so think of the direction indicator in the Cessna 152 in Microsoft Flight Simulator. Okay, you're not staring at the compass to fly a heading, you're using the direction indicator. Now, in most light aircraft with glass cockpits like the 152 that you have, and like most of the aircraft I've ever flown in real life, the direction indicator has to be synchronized to the compass manually every half hour or so, because it tends to wander. In the sim, it stays constantly aligned, but I think you can actually move it. But regardless, whether you're flying using the compass or whether you're flying using the directional indicator, the directional indicator is synchronized to the compass, so you're flying on a magnetic heading. Okay. Now, obviously, you try not to put headsets or anything on the glare shield, but the aircraft still has electronics inside, and it still has a degree of ferrous material as part of its construction. So even without any interference from anything you've put in the glare shield, the compass in the aircraft will naturally point slightly off of the true magnetic heading. Not the true heading, the magnetic heading, okay? And that's called deviation. Now in Flight Simulator, that's not really relevant. We're going to assume that's always 0. But in real life, it's something you need to be aware of, but generally this, you can see the calibration card here, okay? This is all the essentially different headings that if you point the aircraft north, or if you want to fly north, you need to fly essentially -1 degree from north. If you want to fly 030, you would have to fly 031 to actually be flying on the 030 magnetic heading. Okay, it's so minuscule, it's not usually an issue. If it gets beyond a couple of degrees, you'd be taking the aircraft out of service and you'd be putting it in to get the compass looked at. So for flight sim, again, I'm making you aware of it, but it's not something you need to know. Okay. Does that make sense? The difference between variation and deviation?
So this is maybe a dumb question. When does this really? I understand that it matters all the time, right? Because it would be dumb to forget this. But like, when does this deviation really become a problem when you're flying VFR? Like, what's the distance where you're starting to be like, well, I'm flying north, but I'm not actually flying north?
Never really. It
Okay.
never really. As I say, if you've got so much deviation that you're actually having to account for it in your flight plan, there's probably an issue with the compass,
Okay. Cool.
and you would get it fixed.
The most I've seen in an aircraft is about 5 degrees difference, which is significant enough to correct for. But usually these will be older aircraft that were certified before the now times. But as Andrew correctly pointed out, it's rarely an issue, and as Noel, you've figured it out that over the distances of the legs you do in VFR, it's not an issue. This is especially true for Americans who do feature crawling. But it is, as Andrew said, it's really important to know this in terms of the theory and understand why you've got deviation.
All right.
Okay. So that's the basics of compasses and the difference between magnetic and true. The bit that you really need to know is how do I convert between them. So it's really quite simple. I'm going to show you a way that I was taught how to do it. And that makes it straightforward. There's a couple of wee bits you can use as well if you're in the aircraft and you have to do it for some reason. So, the first thing, if you're going to convert between compass and true, is you want to draw out a table, okay? CDMVT. There's loads of different ways to remember this. I actually just remember it as CDMVT. I think there's a wee rhyme, something to do with Cadbury's Dairy Milk making a very tasty treat. I personally don't find that helps me. Sailors do it the other way around, and they do TVMDC. And again, they've got some very interesting way of remembering that, something about virgins. I'll not get into that. But it's the same thing, okay? Now, there's a reason I do it this way around CDMVT, and as it was explained to me. So the first thing, what do these mean? Compass, deviation, magnetic heading, variation, and true. Okay, so it's just a table so you can write out these different things. So let's say we've measured a plot on the chart and it's 219 is the track, okay? So that's our true track, and we read the chart and it tells us that the variation in that area is 2 degrees west. So that's the first thing we'd write down there. Underneath the T for true track, we write 219, and underneath variation, we write 2 west. So, do we add or do we subtract the variation from true? Well, there's a couple of ways to remember this. You can remember that east is least and west is best. I don't really like all these rhymes and sayings and phrases because they don't really tell you what way you do it, if you're going from true to compass or if you're going from compass to true. So the way I was taught by a sailor, my good friend Brune, who, for all his faults in navigation, did teach me some really good things that they do on the ship, and it helped me in my dead reckoning. There's a phrase, cadet. So what this phrase is telling you is if you're going from compass to true, okay, compass to true, you add east. So if you've got an east variation, you would add it if you're going from compass to true. If you get a west variation, you'd subtract it. If you were going the opposite way, if you're going true to compass, it's the opposite way around. So you add west and subtract east. Okay? If you just want to remember it, then that's also equally fine. Whenever I'm doing this, I just think in my head, cadet, compass to true, add east. Okay, right, I'm going the other way, so I must be adding west. Now, again, an easier way that I was taught when I'd done my ATPL ground school was to just draw an arrow in the direction underneath the variation, like this. So it's 2 degrees west. I've drawn an arrow pointing to the left, which by convention is west, and that arrow points to the bigger number, and that's it. So if we had an east variation, the arrow would be pointing right. That would mean the true would be the bigger number. So we would subtract 2. But in this case, it's a westerly variation, so the arrow points left. So that means the magnetic heading is going to be bigger than true, so we add 2 to 219. And that means that the magnetic heading that we want to fly in order to track the true track of 219 would be 221. Does that make sense so far?
The theory of it definitely makes sense. I'm gonna make some flashcards to remember this.
Okay, you'll be getting a shot to actually do it.
This is streaming, so you will have a video recording of all this.
Okay.
Making flashcards.
So again, in Flight Simulator, not really going to account for it, but in real life, you maybe would. So the next thing we need to account for is the deviation. So this is 1 degree east. So what way is the arrow pointing this time?
To the right.
Correct. So then what would be the compass heading that we would have to steer in order to fly that magnetic heading of 221 in order to fly that true track of 219?
Would it be 220?
Yes.
Correct. It is, and I've just noticed I changed the deviation. So it was bigger before, and I've not updated the slide, but well done. It's subtracting because it's pointing to the magnetic heading, so the compass heading is slightly less, okay? So in this case, there's not much of a difference, and the variation and deviation cancel each other out. Okay, some parts of the world though, variation is much more significant. So let's say we're going to fly 045 true track, but this time we've got a variation of 13 degrees east. So what would the magnetic heading be in this instance?
Would it be 058? Oh no, sorry, the other way.
Draw your arrow one. Points to the bigger number, so that
So
means the
yeah, it's gonna
magnetic.
be 02.
Correct. So the arrow always points to the bigger number. Honestly, the day my ground school instructor showed me this, my whole mind was blown. It just made the whole thing so easy because I just didn't get it. As long as you draw the arrow, you're good. Okay, so we've got a heading of 032. We've got a deviation on this heading of 2 degrees west. So what's the final compass heading that we're going to steer?
34.
Let's hope I've got this one right. Yay, 034, correct. So that's it. That's how you convert between compass and true and compass. Obviously, if you're trying to take a compass heading and convert it to a true track in order to plot it, then you would just do it the opposite way around. You'd start with a compass, you'd enter your deviation, you'd work out your magnetic, then apply the variation to get the true. Okay, but it's the exact same. So the last one I wanted to show you was one which can cause confusion if you're in and around north, where the compass obviously resets from 360 to 001. So let's say we want to fly a heading of, or we want to track, sorry, 010, but this time we've got 19 degrees east. So you draw your arrow in, you know that true is going to be the bigger number. So now you have to subtract 19 from 010.
351.
Correct. That's
Yes.
it. All you have to do is do 010 minus 19 and then add 360. If it goes negative, add 360. Okay, you can add the 360 at the beginning if you know it's going to go less than, but if you're doing it in your calculator and you see that, just add it. Okay, and then 3 degrees east. So now the deviation is compounding the variation. So our final heading that will actually steer in the aircraft will be 348. That will be the compass heading. Okay.
Wow, that's substantive.
Yeah.
So that's it for compasses. Any questions before we move on to look at airspeed?
When you do these things in the airplane, do you just, I mean, this is relatively simple, but do you carry a calculator or do you just do it in your head?
You try and do as much in the aircraft in your head. Try and avoid using calculators or computers, but you would have your calculator and your computer on you. Depending on where you are, the variation, if you're not near the poles, the variation is usually quite subtle. The 2 degrees west, that's actually the variation where I fly in Scotland. It's between 2 and 3 degrees. We usually just go for 2 for purpose of calculation. But that's when you remember cadet. If you are having to do this in the air, you just remember compass to true, add east. Then you can work everything else out. So if compass to true means I add east, then if I'm going from true to compass, I must add west. So if you were plotting a diversion, for instance, you would maybe have to do that in your head. But if you know that the variation's so small, and it's you're doing a diversion or something, you probably wouldn't even bother.
Right.
You'd probably just go with what you measure on the chart and you'd fly that heading. At the end of the day, your flying's not going to be that accurate that a couple of degrees is going to matter.
The
Right.
reality is, Martian, most of these calculations are going to be done on the planning phase.
Right.
So
Yeah, that's right. I should have stressed that. This is all the stuff you do on the ground. You do it on the ground for the reasons that we've just discussed. Calculate as much beforehand as you can to save your work in the air. So, anything from you, Noel?
No, this all makes a lot of sense, and honestly, that knowing this would happen on the ground is very helpful because I'm sitting here and I'm like, I don't know the difference between like 1 degree when I'm flying. That's crazy. Like but this is super helpful. Actually, the one question does come up. So if like let's say I knew I was heading, I was flying a heading of 010, like I knew I had to be doing that heading, and I looked at my mag compass and it said something crazy like 1880, you know. Would that be a moment that I was like, and I was 100% sure that I was flying, you know, northeast? Would that be a moment that I'm like, I need to get this thing on the ground because my compass is weird, or is a compass failure not a get on the ground immediately situation?
Compasses generally don't fail.
Okay.
The only thing that I can think that would go wrong with a compass on the ground, your airspeed's going to differ from your true airspeed. Not so much a big difference at lower levels, but at airliners, there's a huge difference there, okay? But it's still enough to take account of when we're flying, even in light aircraft at a couple of thousand feet. So the next one is calibrated airspeed. Now, calibrated airspeed is correcting the indicated airspeed, the speed that we read on the dial, for what we call position error and instrument error. Can anybody have a guess at what position, or if I rephrase it, pressure error might be?
Would the pressure density change with like outside weather pressure, but also just altitude?
Yeah, absolutely. The density of the air will reduce the reading on the. So as density reduces, as you go higher, the effect of the less dense air on the indicated airspeed will result in a lower reading. So you need to account for that. But when we talk about pressure error, what we're actually meaning is that the sensed pressure is interrupted because of the air moving around the aircraft. So the way that an airspeed indicator works is the system takes in the dynamic pitot pressure, which is the pitot that sticks into the air, okay, the pitot tube, and then it subtracts the static pressure from the dynamic pressure. Now the static port is a little silver port that's on the side of the fuselage somewhere. They try and put it somewhere where it's not going to have interference from, say, the wing. Because obviously the way the wing works, it relies on pressure differential to create lift, amongst other forces. So if your static pressure port is near a disturbed airflow, then you're going to get an erroneous reading, and that's going to make the airspeed indicator over or under read. So they do position the static port such that the interference is minimized, but there are instances where you can't do anything about it and the forces of nature are going to take hold and your airspeed is going to differ slightly. So we calibrate the airspeed, and we do that by using a table. Okay, it's in the pilot operating handbook. This one's from a 172. And all this is telling us is with flaps up, if we're indicating 90, our calibrated airspeed is 89. So that when the instrument shows 90, it should actually be showing 89, but there's an error there and we have to correct for it. So if you look at that across the board, it's only a couple of knots. It's not huge. Okay. It gets worse towards the lower end where you're not relying so much on the airspeed anyway. If your approach speed sort of 65 knots, touching down around 55, you're not really getting into the region where it's a massive issue. And because the airflow is different with flaps up versus flaps 10 versus flaps 40, there's different calibration tables for those configurations. Now again, it's something to be aware of. In modern glass cockpits, I actually tried to find out if the G1000 does it. Certainly in airliners, because all of the pressure information's fed through computers, it actually calibrates the airspeed for the pilot. So what they're seeing on the instruments is actually calibrated airspeed. So it's indicated and calibrated at the same time. And the G1000 equipped aircraft, and I don't know if they do that. This table's still in the 172 POH, so I'm going to say that they don't. So there's still a difference between indicated and calibrated. But in any case, the difference is minor. But technically speaking, if you're going to convert, if you want to know your true airspeed, you have to first calibrate it. Does that make sense?
Yeah, makes sense. One question: is the pitot tube, so the dynamic pressure, affected by pitch at all? Because it wouldn't be pointing straight into the airflow, like angle of attack wise.
I'd imagine it probably is Martian. I don't know for certain, but I would expect it would be extreme angles of attack that would result in any issues with dynamic pressure in the pitot tube.
That's correct. And one quick correction, Martian. The pitot tube takes total pressure, not dynamic pressure.
Fair enough. Yes,
Yeah,
yes.
that's how you calculate dynamic using static.
Right.
To answer the G1000 question, it's indicated airspeed on the speed tape, and underneath at the bottom you've got the true airspeed corrected for calibration and density.
Okay, so if you're reading off the tape, you'd still have to calibrate
Yeah, but you
that
don't need
speed,
to. You don't need
but you
to
don't have to.
because at the bottom of the speed tape you'll have a TAS indication.
Okay. No, you sounded like you were going to say you were uncertain.
Oh no, I was indicating that I was certain.
Oh,
This
okay.
is
Okay.
very helpful and very good.
Okay, good. As I say, as you can see from the table, it's a couple of knots difference. It's not really affecting you. More importantly, though, is true airspeed. And the reason that's important is because this is the actual speed. Now, maybe Tariq will time in with some examples from the A320. And your 172 pottering along at 2,000 feet, you're going to have maybe 10 knots of a difference between indicated and true airspeed. Maybe a wee bit more than that if you're getting a wee bit higher. When you're up at 30, 35, 40,000 feet, it's much more noticeable. So you would be indicating maybe 280 knots, whereas your true airspeed could be closer to 500. So it's really important that you recognise that what's shown on the dial isn't necessarily what speed you're actually doing, but the true airspeed is the speed that you need for everything. It's the speed that you use to calculate everything else.
Correct.
So you've got to change between indicated to true.
Yeah, what your example was pretty typical, Andrew, for the Airbus. The other thing I'll say is that Um, Aerodynamics wise, we care about indicated airspeed. That's a little confusing
Mm.
to add in there, but just keep in mind the stall speed will be dependent on the indicated airspeed, not the true airspeed, just to confuse things.
Yeah. The equivalent airspeed, the one that we haven't talked about, that's essentially what the aircraft feels. That's what the aircraft's interacting with is the equivalent airspeed, because that's you correcting for instrument error and compressibility. But again, the reason we don't talk about that is I think generally the rules are if you're less than 300 knots, the equivalent airspeed is the same as calibrated or so close it doesn't matter. It only matters when you go higher. But yes, Tarek said you're flying the plane using indicated, so that's still very relevant for controlling the aircraft, but it's a true airspeed when it comes to navigation that we need to know. And just to summarise all that, when flying low and slow, indicated, calibrated and true airspeed are almost the same in practice, but you should always check to make sure. Now, I'm conscious we're just coming up an hour here. I'm just going to go through some examples of calculating true airspeed and calculating ground speed. Are you wanting to take a break, or are you guys happy to carry on?
I can keep going, but I can also take a break. It's the same to me.
Yeah, I'd say keep going as well.
Okay, cool. We can do that. Okay, so ground speed, what is it? Can anybody hazard a guess?
How fast you're going in relation to the ground?
Absolutely. Not a trick question. Ground speed is the horizontal speed of the aircraft relative to the Earth's surface. Thank you, Wikipedia, for making everything so complicated. It's the speed that you're moving over the ground. So ground speed determines the time that it takes to fly a given distance between 2 points in the ground. So if we're navigating with reference to features on the ground from town A to town B, or lake A to town A, it's the ground speed that's important because it's the distance we're covering over the ground that matters. You can go in 300 knots, but if your ground speed's only 20 knots, then that's the speed that you need to use to calculate the time to get from A to B.
That would be some wind.
That would be a significant wind, Martian, you're correct. So ground speed can be calculated by a couple of means. You can either measure the time taken to fly between 2 points of a known distance. So that's how we would do it the old-fashioned way. You don't have instantaneous ground speed readouts. So you would on one of your dead reckoning legs, you know the distance. You would measure the time taken between those 2 points, and then you would just do the old speed distance time equation to calculate the speed, and that speed that you calculate would be your ground speed. You can also add or subtract the wind component from the true airspeed. So if you know your true airspeed, which you can calculate in the air using a computer, you can, and you know your winds, you can do a quick sum and you can calculate your true airspeed. On modern aircraft, because they have GPS, if you have a G1000 or a GNS 430 or any GPS system, the GPS knows how fast you're traveling across the ground. So you can actually get a ground speed readout. So most modern avionics systems, including the G1000 in Flight Simulator, you'll get a ground speed readout on that system. There is actually one other way that I've not mentioned here. If you tune a VOR with a DME or just a DME, you can get a ground speed readout from that as well. I can't remember how that works. It's very, very technical and confusing. And that's also radio nav, so we're not getting into that. But if you do have an older aircraft and you've got a VOR DME system on board, you could also get your ground speed from that if you're suitably equipped.
A word of caution, that ground speed reading from the DME does not take into account the direction you're traveling in. It's your speed relative to the beacon, to the VOR.
See, I
So
told you it was confusing.
so it's only accurate if you're flying straight towards it or straight away from it. But if you're flying horizontally, if you're flying in a perfect circle around it, it will probably read 0 because you're not moving in terms of distance relative to the DME itself.
There you go. So accurate calculation of your time en route is important for fuel planning. So accurate calculation of ground speed is imperative to what you're doing. Okay. So we're going to go into wind components. Everybody quite happy with the definitions on airspeed, ground speed, true airspeed, calibrated airspeed? It's not as simple as just looking at your speedometer in your car and saying I'm going 40 miles an hour. There's a wee bit more to it.
Yeah, it's good.
Good.
Makes sense.
Excellent. So the next thing we need to look at before we bring all this together is wind components. So winds are a vector. Are we all mathematically inclined in the session today?
Yes.
A little.
Well, it's high school maths, so don't worry, it's not too technical. Like any other vector, you can break the wind down into components. Now, Noel, me and you touched on this briefly in the crosswind circuit training, and this was actually the inspiration for this whole thing, was because what I was trying to explain very badly would have been much more easily explained with a picture. So in aviation, we break the wind down into two components. Okay, we break it down into headwind component, and we break it down into crosswind component. One important thing to note though with these components, because the headwind component or the tailwind component, if you're flying with the wind, and the crosswind component are always defined relative to the aircraft, then the magnitude of these components are different for any given direction of travel with the same wind. And it makes sense if you think about it. If you're flying straight into this wind, you're going to have zero crosswind component. If you're flying with that wind coming straight across the aircraft, you're going to have all crosswind and no headwind. So let's quickly summarise the components and then we'll look at some examples. So only the headwind and the tailwind component can affect ground speed, and this is why we break it into components. Okay, because headwind and tailwind affects ground speed, but not drift. But crosswind affects drift, but not ground speed. So we need to know these components. We need to calculate our ground speed, and we also have to calculate our drift based on the winds. So it's important to understand the breakdown of the vector into its components. So you can calculate drift and ground speed mathematically using basic trigonometry, sine and cosine. But pilots generally don't have the time or the patience for that, so we use computers, flight computers specifically designed to do that job for us. And by applying the wind vector to the intended track, it will give us a heading to steer in flight to counteract the crosswind component. Actual drift has to be calculated, or not calculated, but checked at regular intervals to ensure that we're still flying the track that we want to be flying, and we need to adjust the heading accordingly. But we will, before the flight, calculate what our heading should be to counteract the wind. So it's a lot of words. Let's have a look at some examples. So let's say we've got a wind 03025 knots. Now remember, the wind always is reported as the direction it's coming from. So you might be saying, Andrew, are you silly? That wind's not pointing towards 030. It's because it's coming from 030. I will also take this opportunity to explain that these vectors aren't drawn accurately. They're just figures. So they're not going to be representative of the actual components. I had to actually tweak them a wee bit to make them look right, but that was the most important thing. So let's say we've got, we're flying along at a heading 090 and our true airspeed is 110. Does anybody want to take a stab at what this wind's going to do to our track relative to the heading and our ground speed relative to our true airspeed? Is it true airspeed going to be more or less than the ground speed?
The true airspeed is going to be less than the ground speed.
You think?
No, sorry, it's the other way around. Yeah, no, it's gonna read higher, but it'll actually be lower. Yeah.
Martian?
Yeah, ground speed is lower, and we're gonna drift to the right.
Absolutely. So if we draw this out as a vector diagram, remember high school maths, this is as advanced as it gets. And then we draw it from our origin to the nose of the wind vector, that will give us our track. So we will be tracking to the right, but our ground speed will be less. And the reason for that is most of the wind coming at us is a crosswind. The crosswind component is 22 knots. But there's only a small difference in head true airspeed versus ground speed because because of the angle of the wind relative to our heading, we've got a very small headwind component. But it's still there, and it still makes a difference because now our ground speed's 100 knots as opposed to 110. And if we were to look at that, how does that look for an aircraft? Well, our nose is 0.090, but over the course of the flight, we're going to get pushed this way, even though the nose is still pointing. So remember, Null, no rudders, we're flying coordinated here, but we're getting pushed off course.
Gotcha.
Okay, so let's say we're going in the exact opposite direction, 270 with the same wind. What do you think is going to happen in that instance?
Well, ground speed's gonna be higher by 13 knots, and yeah, crosswind is the same. We're gonna drift to the south, left in this case.
Null, do you concur?
Yeah. The crosswind won't change, but the headwind will switch to a tailwind and will be or the ground speed will be faster.
Spot on, that's exactly it. So again, if you draw your wind vector, we've now got a track of 260, so we're 10 degrees off course. Our ground speed's now faster than the true airspeed. Okay? Because we're now going with the wind. Now that's a major reason why aircraft choose the altitude they're at, because if you can climb 2,000 feet and drop from a 50 knot headwind to a 20 knot tailwind, there'll be a significant saving in time and fuel. And that's the reason the North Atlantic crossings are run the way they are, because every day that they look at the forecast and they forecast the routes to make optimal use of tailwinds for the eastbound crossing and minimize headwinds for the westbound crossing to try and maximize efficiencies. So just because even with the same wind we've turned around, we are now getting a faster ground speed. Okay, and again, that will just look like the aircraft will still be pointing west, but it's getting pushed southwest. Just more of the same. 060 for flying sort of northeasterly this time. So we'll get a much greater effect on ground speed now because we're more into the wind than across it. Okay, so this time we've got 13 across and 22 knots headwind. Okay. Again, if we fly due north, we're almost right into that wind, so we're getting, but that should say ground speed, I do apologise. A ground speed of 89 knots. So the components are slightly different. Okay. The reason it looks the exact same is because I've rounded these. They're not, I think it's like 12 and a half, and that's probably more like 13 point something, which is why the ground speeds are not different. Okay, don't get too hung up on it. This slide's more just to show how the wind changes, or the components of the wind change with your heading. Okay, so last one flying southeast, you're going to have a nice big tailwind there, not so much of a crosswind, but you're still going to get blown off track if you don't correct for it. Does that all make sense?
Yeah, I'm curious how you actually apply it to flying, because yeah,
Oh, well,
Hard
don't
saying.
worry.
hard to do in your head.
We'll get onto that. We'll get onto that. So, if we look at the aircraft, let's look at some scenarios. I'm just thinking while I introduce this now. Let's have a wee look. I've got a computer here as I promised you. Just wondering if it's the best time to bring it in now. Yeah, let's do it, I suppose. So, what altitude and speed are we at?
You're at 1,400 feet, and your airspeed is what looks like 109 knots.
I'll go for that. 110 knots, and we're at 1,400 feet. So let's first calibrate the airspeed. Okay. So what's our calibrated airspeed? We're flying flaps up. We're in the cruise. What is our calibrated airspeed in this instance?
108 knots.
Excellent.
Agree.
108. So slightly less than our our indicated airspeed. It's not going to make a huge difference. But we need to know our true airspeed. So how do we do that? I'm just going to bring this calculator over here. So this calculator, you're going to get a shot at using this yourself in a minute. But the answer is, this is how pilots do things. There's some rules of thumb, but for things like true airspeed where you have to account for density and other things, you would just use a calculator. Okay. So we want to know our true airspeed. So we would put in the things that we do know. So our pressure altitude, our altitude at 29 or 9 or 2 or 1013. In this case, the altimeter's set to that, so we can just fire it in as is. So 1,400 feet. Okay. We need to give it our calibrated airspeed. So that's why calibrated airspeed is important, because all the true airspeed calcs are based on our calibrated airspeed. Okay, so that's 108. Now straight away that comes out with our Mach number. It must be assuming the airspeed out, or sorry, it must be assuming based on standard altitude. So the outside air temperature, I've not given you that information. I probably should have, because what you would do is you just look at the outside air temperature gauge in the aircraft, okay, and you would put that in. And the reason that affects the aircraft is because the density change. And that's what Null picked up on earlier. So if the air's less dense, if it's hotter, the air will be less dense. So the airspeed indicator will be under reading more. If it's really cold, the air will be more dense, so the airspeed indicator will be overreading a wee bit more than it otherwise would be. So I think 1,400 feet, we are going to be about 12 degrees outside if we were to use 12 degrees Celsius. So if I just put in 12 degrees Celsius, boom, there you go. Okay. True airspeed's 110 knots. So the calculator does all of the technical things for you. So all that stuff we explained about position error and density error, compression error, all of that is dealt with by the calculator. And it tells you, if you can feed it the information you know, it'll tell you your true airspeed. Okay?
Is that emulating a phone app?
What's that?
Is that tool you're using emulating a phone app?
No, this is a CX3 flight computer. I've actually got one sitting on my desk. It's an actual computer. It looks like a calculator. It looks like a mathematical calculator, a scientific one. Sorry. I got one of these. I keep one of these in my flight bag. I've also got an old-fashioned analog calculator, a CRP5. No, you'll be using an E6B, but it's the same thing. This is still a computer. It's just analog. But and being in the aircraft, the CX3 is much better. And this is the only thing I've got an emulator for, so it means I can give it to you guys.
And as EASA pilots who have done the theory with the CRP5, we hate it with a passion.
Although if you've done your exams with Ostro, you could use one of these in your exams.
Bastard.
Tarek had to do his ATPL exams with one of these horrible things. I got to use a nice modern electronic calculator.
I
Do the
had
exact same
the
thing.
predecessor of this one, which is so much more basic, and I wasn't even allowed that.
Shocking.
I
Keep
know.
us in the Stone Age as pilots.
Absolutely.
So that's it. That's our TAS. Okay. And then if we had a headwind component of 10 knots, the ground speed would be TAS minus headwind component, which would be 100 knots. So the actual speed would be 100 knots across the ground, which would be for navigation, the speed we're interested in. Now this calculator would let you calculate ground speed as well, but that you would likely be doing that ahead of time on the ground. But if you were unsure, if the winds had shifted, you might want to recalculate. So you could certainly use this technique if you understand it. So the next one here, does anybody want a shot of doing it?
Be sure to link the calculator
Ooh.
in the general section so Nolan and Martian can get access to it.
Where do you want me to put it, Tarek?
Just in the general, I guess.
Resources, maybe?
Resource.
Yeah.
Yeah,
Good idea.
do resources. You should have permission. Yeah, there you go.
Don't worry, you'll both get a chance to use this calculator. So if you want to open it up, you can either do it between you or do one each, okay? So this time, what's our indicated airspeed and our altitude?
Oh, so
Not a
I'm
trick
just
question. Not a trick question.
Ah, right.
I did the last one. You should grab it.
On you go, Martian. You've been put up for it.
Yeah, 6,500 feet. And we're at 110 knots again.
Excellent. So we are indicating 110 knots again. So without even looking at the calibration chart, what's our calibrated airspeed going to be?
108.
Correct, because it's not affected by anything other than the aircraft configuration. So calibrated airspeed once again is going to be 108. Now, not giving you it, but let me just calculate what it will be. Okay, so the outside air temperature is 2 degrees Celsius, that is. So who's got the calculator open and wants to have a go at calculating true airspeed?
How do I set it to Celsius? It's on
There's a button called Set Unit underneath the star. You press that, that will change it to from freedom units to sensible European units.
Yep. Okay. I have a true airspeed.
But do you make the true airspeed?
108.9, so about 119 knots.
Let's just have a wee look then. Oh, that looks like a Microsoft Flight Simulator true airspeed, or outside air temperature. 285 degrees. So, Null, did you calculate it?
No, because I input the CIS and the TAS section, and it took me a disturbingly long time to figure out how to delete something.
That's okay. They use the clear and the backspace buttons.
That's where I got to. How would you say the outside air was? 2?
2 degrees Celsius.
Gotcha.
That would be the international standard atmosphere temperature at that height.
RC is clear, okay. Right.
So you sticking with 119, did you say, Martian?
Yes.
Good. Wait until Noel's got his answer in. Do you want us to run through it together?
No, well, it's changing my calculated my CIS. It's not giving me a TAS, which is confusing.
So you need to feed it. So let's just go through it. If you look at the presentation or look at my screen,
Yeah.
I can quickly go through it. Okay, so make sure everything's cleared. Okay,
Yep.
Start at the bottom. So put in what we know. So we've got 6,500 feet. So 6,500 equals to enter. calibrated airspeed, 108. It saved it from last time, so we can just hit equals. And then it's outside air temperature. So what did I say? 2 degrees Celsius.
Yes.
Press equals,
Yeah. Okay.
and then it auto-populates the rest. 118.9.
118.9. Yep.
Okay.
I got it now.
Super. So true airspeed 119. This time we've got a stonking tailwind, 30 knots. So what's our ground speed going to be?
Thirty knots.
Do we?
You can use, I think there's a function in the calculator to do it, but if you know the component and you know your true airspeed, then ground speed is task plus tailwind component. Because we're with the wind, so we add it this time. So ground speed's 149.
We're going 149 knots.
Across the ground, even though we're showing 110 in the cockpit.
Damn.
So you see why it's such a good thing to get into a tailwind if you can. It's not good on landing, and that's one of the reasons why it's not good on landing. It's because when the wheels touch the ground, that's the speed they need to get up to. So you'll be going much faster on over the runway. That's why we always land with a headwind. But in the air, you want a tailwind if you can get it,
Gotcha.
because it can make a significant difference. And again, if the fuel economy justifies it, if you don't fly a 40-year-old 172 that can barely make 500 feet per minute at sea level, then you don't really want to be going up to 6,500 feet. If you've got a nice brand new Bonanza, then get way up as high as you can go, because if you can get that true airspeed up, your ground speed's going to increase as well, and you're going to get there faster.
Gotcha. As noted, there's actually a video that came out from one of the YouTubers. I forget his name, but he went into Microsoft Flight Sim and he tried to get the Cessna 172 as high as it could physically go in the simulator by like messing with mixture and like really pushing it to like the absolute edge. I think he got it up just shy of 16,000.
Yeah, I mean, I think that the official ceiling for a 172 is about 13,000, 13,500 feet. I wouldn't be surprised if you could nudge it a wee bit higher. The 172 in the sim, when it comes to performance, it performs by the book. So it makes it really easy because you can just read the POH, the Pilot Operating Handbook, and you can get all the performance figures. In real life, the aircraft gets old, the engine makes less power, the paint gets a wee bit rough, so you lose a few knots due to aerodynamic drag. There's a number of factors, but the by the book figures is what the plane gives you in flight sim. It's not a bad thing, but it's not necessarily what you'd experience in real life. So different aircraft have different characteristics, and some of them go faster, some of them go slower. Okay, so that's us almost done with the sort of prerequisite theory. Just got a quick bit to talk about fuel and time management, and then we're going to actually look at planning a flight. We're about an hour and 15 in. Does anybody want to take a short break, or do you want to continue on? I'm happy either way.
I'm to continue, but if you need a break, that's fine.
I'm okay. Null,
Yeah, let's roll.
happy to go. Cool. See, I've been scouring Google for all these pictures, can't you? So, fuel and time management is an important, very important thing when you've got limited fuel on board, okay? So light aircraft generally have fuel tanks sufficient for 4 to 5 hours of sustained flight. Some will do more than that, some will do less than that. But generally speaking, that's the sort of range you're talking. However, there's always a but. Most light aircraft cannot fly with both full tanks and a full payload and remain within mass and balance limitations. Null, I think Tarek said he had done some mass and balance theory with you in the past.
Yep. We had a day on it.
So you'll be familiar with that then, that you need to be careful. I mean, to a certain extent, it also affects transport category aircraft as well. You'll see if you look at the figures for airliners, you'll find that there'll be a maximum ferry range, and there'll be a maximum range with max payload on board. So a lot of even airliners suffer from this problem where they can carry more fuel than would be permitted with a full payload on board. So the payload.
Sorry, when I was doing survey, I was flying an aircraft with extended fuel tanks and a lot of fancy avionics. And so even with a single pilot and no survey equipment, we couldn't fill it up full tanks. In fact, we couldn't even fill it up full tanks with no one on board because of the mass imbalance issues. You'd exceed the maximum weight of the aircraft.
Yeah, and that's an interesting point. A lot of the time when aircraft are flown, light aircraft are delivered from America to Europe if they're being delivered from manufacturer, or vice versa. What they'll do is they'll take out the back seats and they'll install a big bladder tank, and that'll allow them to carry lots more fuel than they would normally. In some instances, it would put them overweight, but there's certain cases where you can apply for dispensation from the FAA to actually fly the aircraft overweight if it's a one-off for ferry purposes. But generally speaking, there's a maximum takeoff weight, and that's set in stone, that figure, unless you've got a dispensation for it and a good reason. So we have to be careful with payload. We need to know the distance to be flown and the fuel that we need in order to ensure that we can operate the flight safely. The other issue we have with these old planes, or these light aircraft, is that the fuel gauges aren't very reliable. So it's really important to know your fuel load before you take off and also know how much your aircraft burns. You can use the fuel gauges as a rough estimate, but the reality is in real life, you'll get in a light aircraft and there'll be a placard next to the fuel gauges saying fuel gauges are unreliable, or they just don't work.
Even when you don't have that placard, one of the instructors I used to fly told me the best thing fuel gauges are for is to tell you if you have a fuel leak. Basically to see how fast the fuel tanks are emptying. Fuel gauges are reliable at 2 points when the fuel tanks are full and when they're empty. Anything in between is extremely inaccurate.
Okay.
The general, you know what aircraft, when you're flying an aircraft, you'll know what it's burning. So that's why you calculate the fuel that you need. And then as you go, you can just work out, well, I've been flying for an hour and 15. I burned 6 gallons an hour, so I've probably used about 8 gallons or so. It's as simple as that. It doesn't need to be too complex. So what is the fuel that we have to carry? There's quite a few different things. Okay, we've got trip fuel, we've got taxi and takeoff fuel, we've got alternate fuel if we need to divert. We've got contingency, which is just essentially accounting for any errors in your calculated fuel burn, and it's a percentage of the trip fuel. You can then elect to carry additional fuel on top of that if you choose to, and you've also got a final reserve. Now, out of all these things, it's down to the pilot to choose what they want to take. But the reserve fuel is usually, as far as I'm aware, in every authority a legal requirement. There's a minimum defined, and under EASA, the European regulator, the UK now being a separate entity, and the FAA, the American regulator, that is no less than enough fuel for 30 minutes of sustained flight at the cruise speed by day, or at night 45 minutes. So you must arrive over your destination with no less than 30 minutes of fuel remaining in the tanks, or 45 minutes if it's a night flight. So it's fairly unambiguous, fairly robust, not much to really question. So that's what you're planning. You need to make sure you arrive with at least that amount. Otherwise, you're breaking the rules. And you're also flying unsafely. Okay, so that is all of the prerequisites to actually planning a flight. What we've covered there would normally be covered in probably half a dozen different lessons, so it's very much condensed. do I have any questions from anyone before we then look at what we came here to do, which is navigation? Excellent.
Negative.
Good. So, planning a flight. What do you
Oh, one question. So you keep changing your power settings in flight. Do you just assume an average burn rate, or do you have to take that into account?
It's in the POH. Minor changes in power at cruise to maintain a constant RPM aren't going to change the burn rate significantly. The biggest impact you can have on burn rate is forgetting to lean the mixture if you're flying at a high enough altitude for that to really matter. Takeoff is going to be your takeoff and initial climb out is going to be your biggest factor because the engine's operating at full power. It's going to use significantly more fuel for the climb out than you will at cruise. But the POH has tables in it that tell you basically how much fuel you'll use in the climb based on, I think it's the time, it may be the altitude, but either way, there's tables in the pilot operating handbook that tell you how much fuel you're to assume that you're going to use in the climb out. And if you've got any additional climbs planned, if you're going to have to climb over, say, terrain halfway through your flight, then you would just need to account for that in your planning. But generally, minor power changes at altitude aren't going to cause any significant change to your fuel flow.
Okay.
Okay. Great. So, how do we plan a flight? You're going to need quite a few things here. You're going to need a sectional chart. You're going to need a square protractor so that you can line it up with the grid lines to make sure you've got true north. You're going to need a ruler, a scale ruler, so that you can measure in nautical miles without having to do any conversions. You're going to need a flight computer. Null, when you start your training, it'll be one of these bad boys. This is an E6B.
Woo.
I believe this is the original flight computer. The CRP5 is the sort of UK or European equivalent. Very much the same, slightly different layout. Or a CX3 or any other flight computer that you happen to have. Again, we're going to use a CX3 because you guys can also use it. You're going to need a plog so that you can write down your flight, turning points and all the other good stuff that goes with it. And you're going to need a calculator for a couple of other bits and bobs. Or, instead of all that, you can just use an online or an app that's a VFR flight planning tool. There's loads. Tarek pointed out there's one called SkyVector. So when we come to actually doing the flying part of this, I would recommend that we do it on SkyVector. Somewhere in the USA, because they've got all of the sectional VFR charts available on there, and it basically does all this calculation for you. I use an app in the UK called Sky Demon, which is what most VFR general aviation pilots use in the UK. It's very much the same thing.
In
You
Europe,
could,
in
all you
fact.
have to do in Europe as well, Tarek, is that what
Yeah,
they use?
yeah. In the US, the equivalent is 4Flight.
Yeah, there you go. And the benefit of these systems is you can very quickly plan a flight. You'll see that this can take some time to do it the old-fashioned way. You can also tweak it as you go, and you can also monitor your actual progress against your plan. All of these things have only kind of came about in the last 10, 15 years. So the regulators haven't quite caught up. That's why we still have to do it the old-fashioned way. I'm sure they will introduce navigation apps and GPSs at some point, but right now this is still how it's taught. So let's talk about turning points. So the turning point is a waypoint essentially. Okay, that's the VFR name for it. It's the point that you're trying to navigate to along your flight. So you're going to go from A to B. You're going from one airfield to another, but along that course, you're going to have a series of turning points. Okay, so these are things you have to recognize in the air so that you know where you are. So what do you need to consider when you're picking turning points? Well, it's got to be a large, obvious target. Remember, you're typically 2,000 feet or more above these things. and sometimes you'll be in less than favourable weather with fog or just poor visibility in general. So you need to pick something that's easily seen from the air. Now, one common mistake a lot of new pilots fall into is using roads. Roads are useful, especially in pilotage. You can follow a road if you know where it goes, but don't over rely on them. If a crossroad on a map might look very obvious, but when you're in the air, that might be very difficult to see. Okay, unless it's a major road, a highway, or a big junction or something on the road or an intersection, don't over rely on it. If you've no other options, you've no other options, but it just makes things difficult. Okay, what you're looking for is distinct shapes like towns, woodland areas. You can have man-made objects like bridges, wind farms, smokestacks. Smokestacks, especially if they're on the chart, are really useful because it not only gives you a position, but it lets you see the wind because you can see the direction of the smoke.
Oh.
Natural features like lakes, estuaries, coves, bays, large rivers, any of these things you can also use as long as it's really quite an obvious shape. Okay. So we're going to now look at that plog that first came up, or that chart that first came up at the very beginning. Okay. So can you all see this clearly? I can zoom in a wee bit just to go over it. Can
Yeah,
you
that's better.
Yeah, I can see it.
excuse my handwriting? As I say, this was an actual flight I'd done, and I just used the chart. Some of the markings are a wee bit worn off, but it's sufficient. So I'm flying from Dundee to Glasgow. Okay, you've both flown in Glasgow in Flight Simulator. The airport's just over here, off the left of the screen. Okay, but this portion of the flight I'm doing using dead reckoning. When I get to Bayliston, I'm going to then use unconventional means to get to the airport because I know the area. Okay, so look at the points that I've picked. So the first one here, Errol, is an airfield. Okay, so it's really obvious to see this from the air because it's an old RAF airfield with the 3 runways and a triangular configuration, and it's sitting in amongst grass. So the runways stick out a mile because you can see the sort of concrete against the background. My next turning point is Balado. Okay, now Balado itself isn't necessarily an obvious airfield. Okay, there's a microlight airfield down there. But what around about Balado might make that a good turning point, do you think?
The lake, maybe?
Absolutely. There's a motorway or a highway intersection here. There's a lake with a very distinct shape, and there's a town sitting just west of it. So all of these factors mean I can very easily start to go through a process of elimination to make sure I'm going where I want to go. Okay. It's also, if you look at the relief, it's in a relatively flat area with some hills to the northwest. So again, that should really help to locate where I want to get to because I know that I shouldn't be flying with the hills on the left. The hills should be on my right. And I know that I should be seeing a large lake with a town next to it and a big motorway junction. So even if I can only see the lake and the town and I can't see the junction, or if I can only see the junction and the lake and not the town, I've still got lots of good references. Okay.
Mm.
The next turning point I've picked is Stirling. Again, who wants to try and identify some of the features around Stirling that might be useful for me trying to find it?
Well, it's going to be built up because of the yellow part, and then you'll be heading into a hill with some wind farms on it, which will probably be pretty easy to see.
Yeah, excellent point, Null. The wind farms, that there's quite a lot of them in the UK now popping up, and they're really obvious. You can see them away off in the distance, and it really helps to get that positional fix.
Just
Anything
real
else?
quick, this M-like symbol, that means mountains?
Whereabouts?
Yeah, those vertical triangles, like.
Those are wind farms, the vertical triangles.
Okay.
It's going to take me out a zoom, but are you talking about
Yes.
these triangles? Yes. So
Yes.
can you see wind farms
Okay.
next to them? So they're dotted all over the place. If you start to look, you'll see them everywhere. There's other vertical ones that are. You can see they've got the sort of flashing symbol on them. That just means they've got a beacon on them.
Right. Okay.
Okay.
Sorry, more specifically, it's tall man-made objects, so it's above a certain height above the ground. They'll be
Yeah.
depicted on charts. It's just that because it's Scotland, in this case, almost every single one of them are farms. So if you look right in the center of the bottom of the screen, you see Polmont, and right above it, you've got a flare stack. So that has the same symbology, but it's actually something else.
Right. Okay.
So,
Okay.
but yeah, absolutely. Sorry, just thought I'd
That's okay.
point that out.
Is there anything else, just before we move on to the next one, around Stirling? We've got the wind farms, we've got the fact that it's a very distinct built-up area. Any other features that might be useful to identify that we're at Stirling?
The river, maybe.
Yeah, absolutely. So see that windy river, it's a very distinct shape, and it runs right through the city. And then, as well as that, you've got this motorway that runs north to south. And you can see that as well from the air. More so probably if you're approaching from this side, from the west. Okay. Now the last turning point isn't great. Can anybody think of some reasons why it's not a good turning point?
You get so much city around it. It's probably hard to say
Yeah,
which part of it you're in.
absolutely. It's just one area. Baillieston is an area within Glasgow, but from the air it just looks like one big mass. It's very difficult. When I was learning to fly, Harriet could always find it because he lived there at the time, so it was dead easy for him. Poor old me, that's from the other side of the city and didn't know anything about the East End of Glasgow. I couldn't tell Baillieston from East Kilbride from Hamilton. They all look the same. So, can you think of a reason why I've maybe used this, even though it's not a good reference point?
Well,
Because if you, oh, sorry, go.
yeah, go now.
Well, there are lots of other good reference points near it, and then if you had kept going, you would have been, I mean, I guess depending on your altitude, heading towards hills and wind farms.
Yeah, I mean that's a valid point, but the reason that I've chose this is because this is the standard entry point at Glasgow. This is if you're approaching from the east, they usually want you to enter the control zone at Baillieston. So it makes sense to use it as a turning point, but it's very difficult. Basically, the way that we identify Baillieston is there's two major intersections on the highways in this area, and it's the northernmost one. That's the only real way to identify Baillieston is the intersection on the highway.
Hmm.
Okay. Um, and it's purely for reasons of air traffic control. If they're not busy, they'll quite often let you go on a direct track into the zone, but generally speaking, they'll want you to come down here. Now, speaking of controlled airspace, can you see all of these blue dashed lines and sort of shaded areas? These are all controlled airspace. So you can see how it can be really important to make sure you're not busting airspace. Because if I fly into Glasgow's airspace by accident, I'm gonna get in bother. Okay, it'll be reported, and there's a chance that I could have my license suspended. I could have to do further training, amongst other things. Okay.
Sorry, just quickly. This is for us in the UK, because in the UK the CAA are ball busters.
Yes.
In Europe and in the FAA, they're a lot more lenient, and there are many channels you can go through to make sure you don't get into trouble.
Yeah.
Welcome to freedom, guys.
So
In
in the
fact, they're
US,
so.
uh,
I was just going to say they're so bad. I know of two people that were flying VFR and they actually clipped right here, Edinburgh's airspace, and they get reported for it. They were in by about half a mile, if that, and they got reported for it.
yeah.
Damn.
Oof.
With the US, you can file a NASA report, and it is almost a get out of jail free card. And it's basically it's a safety report. And as long as it wasn't gross negligence, like you can make some very serious mistakes, and as long as you make a NASA report, you're pretty well protected. As long as there's no evidence that you were being an absolute numpty or you did it on purpose or something. So
Isn't that
yeah.
sorry? Isn't that the thing where like I was reading or listening to one of the podcasts and someone was like, I had to bust into Bravo airspace, but it was because I was avoiding clouds, and they were just like, yeah, it's fine.
Yeah, I mean, I mean, it's in that case, it's a good idea to file a NASA report, but that person was still within the legal limits because there are regulations specifically saying a pilot in command can violate any air law in the name of safety.
Hmm.
Yeah, that's the going back to the old adage of aviate, navigate, communicate. You aviate first and foremost, and if that means leaving an assigned heading or altitude because there's an issue with the aircraft or there's something wrong, you do that as a pilot in command. If you have to bust controlled airspace to avoid a collision, you do that and then you communicate it afterwards. It's very much something that's upheld across the global aviation community, that safety takes priority. And if you have to do something, you do it and you ask for forgiveness later.
I don't know if you're American, that doesn't asking forgiveness. That doesn't sound like us.
Maybe if you're Canadian.
If you're Canadian, definitely. Sorry.
Canadian, you ask
Sor-
for it before, during, and after, right?
Sorry. Right, okay, so that's our flight. So it's a fairly short flight, okay? And as you can see at either end, I'm using unconventional nav. I'm going from Dundee to Errol just by flying the rough direction, and then I start my dead reckoning from Errol, and then I stop my dead reckoning at Bailiston, and I'm again back to unconventional nav from Bailiston to Glasgow, okay? That's fairly typical when you're doing something like this, that you would pick up your navigation from a known point rather than trying to do it from leaving the airport, because the problem with that is you've got to take off, you've got to climb. So if you start at the airport and go to somewhere else, all of it, straight away your calcs are all going to be off. So it's always a good idea to pick up from a known place. So this is a nice little simple flight. And we've discussed the reasons why we have the turning points that we do. We're avoiding airspace, we're avoiding terrain, and we're trying to work with ATC. Any questions so far?
Nope.
Good. So let's do something that is quite important. First and foremost, draw the wind on the chart. By drawing the wind on the chart, okay, so I've drawn an arrow and then I've actually written the winds below it. You would get this information from a forecast. I believe, well, in the UK certainly, you get it from the Met Office. They publish sort of, I'm trying to think, it's probably a couple of times a day they publish the winds in different areas of the UK and Europe at different altitudes. Okay, so we're going to be flying at 2,000 feet. So I've went and got the 2,000-foot forecast. In the USA, I believe there's a phone service you can use to get weather. I don't know if they give you winds aloft, but there'll be an equivalent to what we have in the UK. And likewise for you, Martian, if you were ever doing this, there'll be a German equivalent. There's
Yeah,
usually
sure.
a national service that will give you this info. But by plotting it on the chart, it gives you a good indication of what to expect. So we know between Balado and Stirling, we're going to have virtually a full crosswind. So we can expect the potential to be drifting a lot, and we can expect quite a large correction. Okay, whereas the other legs, it's not as bad. It's still a crosswind, but it's not as bad, you know, between Stirling and Baillieston. Okay, so it just lets you, it's a gross error check. And it's a bit like what you were talking about earlier, Null. What if I know I'm flying north, but my instruments tell me I'm flying south? Well, if you know the winds are coming from the southwest, you can anticipate what the aircraft should be doing. And if it's not doing what you think, if you're drifting south rather than north, there's a sure chance that the winds aren't as forecast, and you're going to have to do something about it. Okay,
Good to know.
so let's populate on the plog the things we know. Okay, so we get the pilot's name, get the aircraft, the date of the flight, in international format, year, month, day, I might add, just to avoid any international crises between the Europeans and the Americans. We've got the from and to, so we're going from Dundee to Glasgow. I've calculated the distance already, and then I've written in here what usable fuel. So we get 30 US gallons on board, and we're going to burn 8 gallons per hour. Okay, that's a fairly standard figure for a Cessna 172. You would get that information from the pilot's operating handbook if you didn't know. Otherwise, if you're familiar with the aircraft, you would know what it burns. Okay, but that's just there for reference. So then we write the turning points. So for each row, we've got from and to. Being the lazy person I am, I never duplicate the two. I always just write inverted commas. So from Errol to Balado will be our first leg. From Balado to Stirling will be our second leg. And from Stirling to Baillieston will be our third and final leg. So next, we can populate the things we know. And this is all just from the chart. This is before any calculations. So let's stick the wind in there. The wind's 140 at 19. Okay, so that's the same. We're going to fly at 2,000 feet. That'll be our cruising altitude. So we put 20 in there. Big 2, small 0. Just shorthand for 2,000. The next thing we then want to populate is our true airspeed. Now, again, we're going to be flying at 110 knots true. We've already calculated that. Flying about 2,000-3,000 feet, your true airspeed is virtually going to be your indicated airspeed as we calculated. If you're going to be a bit higher, you'd maybe want to double check what your true airspeed is going to be. If you get a really hot day or a really cold day, you'd probably want to double check. But if you've done this a few times before, you generally know what your true airspeed is going to be. And for a 172, 110 is not a bad figure to go with. Okay. So there's one more thing on here that we need to kind of look at called safety altitude, or safe alt as it is on the plog. Can anybody take a guess at what that might be, safe alt?
Is that the minimum altitude for terrain?
Absolutely. Spot on. So safe altitude is the altitude that you would need to fly at with a margin of error in there to avoid the terrain. Now, we get that from the chart. Okay, so if you look here, can you see this big 3, 4?
Yeah.
That tells us the highest thing in this box is 3,400 feet. And we add 500 onto that for safety. Okay, so if we are flying in this box, which we will be on this leg, then our safe altitude would be 3,900 feet. Now, that's only really relevant if we fly into clouds. If we get ourselves into trouble and we end up in IFR conditions or IMC, it would be a good idea for us to climb up to 4,000 or 3,900 feet. And that way we can be certain that we're not going to hit anything. Now, there's a lot of reasons why you wouldn't do that, but that's the purpose of it. Okay, so you can have a cruising altitude lower than your safe altitude. And generally speaking, we always do, especially in and around terrain like this, if you're flying through valleys and things. So let's populate the rest of what we know for the first leg. So the safe altitude's 2,600, so there's the big 2-1 here. Add 5, 2-6. The track we've measured from the chart is 219, and the distance, written in green below, 15, 15 nautical miles. Okay, let's do the same for the rest. So Null, do you want to give us leg 2? What's the safe altitude, the track, and the distance?
Safe altitude. I'm trying to find it in the box. Is it just the
Alright,
same for 3,400 plus 5, so 3,900?
yep. And what about the track and the distance?
Is that what you wrote there, the 248?
Yep, absolutely. And the distance is underneath it. It's a wee bit hard to read because it's in green.
It's at 1.7.
17, correct. Now I think I've got the safe altitude wrong because it's the same as the next one rather than being where it should be, but that's fine. That doesn't matter. So we've got that, and then for the last one, Martian, do you want to give us leg 3, safe altitude, track, and distance?
Okay, so well, you already said for one, so I'm gonna assume that that small clip into the top matters.
Yeah, that's been overly cautious. Technically, we're going to fly through this, so there's a chance we could fly through it. So we use the 3.6.
Okay, yeah, so that's 4,100. Then the track is 199.
Yep,
And this 16 miles.
absolutely. So 4.1, 199, and 16 miles. So that's everything that we know from the chart now transferred onto that plog. And you'll notice that makes up most of the plog. All we really need to calculate now is the heading, the true heading, the magnetic heading, the ground speed, and the time. Okay, for each leg. So I'll show you how to do the first one, then I'll give you both a chance to do a leg each, and I'll explain how it's done. Okay, so there's a couple of ways you can do it. There's a few functions in the calculator that you can use, or in the computer that you can use in here separately. But one of the great things about this computer is it's got a plan mode, and you can actually add, I think, 5 legs, and it carries through things like winds and true air speeds for you, so that you don't have to add too much. So once you do the first one, you can then fairly quickly build up a flight plan. So if we go for, I'll show you how to do this, and then I'll give you a shot. So let's populate what we know. So the distance, 15, okay? The true course, measured from the chart, is 219. The true airspeed that we already predetermined, 110. Okay, the wind direction is 140. The wind speed is 19. Now it's asking us for variation, deviation, and fuel flow rate and departure time. Now these are all optional. Okay, if we go down here now with what we've supplied, we'll already have a lot of information here. Okay, so it's telling us that the wind correction angle is -10 degrees. So therefore the true heading that we need to fly in order to track 219 is 209. And it's also telling us that our ground speed is going to be 105 knots. And it's telling us that the ETE, the estimated time en route, is going to be 8 minutes and 35 minutes. So that checks out. It's a 15-minute leg. We're doing around about 100 miles an hour. So it's going to take us just less than 10 minutes. Quick mental sum. you know, you're going to be doing about 1.5 miles a minute.
I couldn't do that that quick because knots and miles are not what I usually deal with.
The key to anything aviation, Martian, as soon as you remember that 60 knots is 1 mile a minute,
Okay.
We're
you've
talking
cracked.
about nautical miles here, not
Yeah,
statute miles.
everything here is knots and nautical miles. So
Oh, that's how
60,
knots is defined. It's 1 mile per second. 1 nautical mile per
yeah, a knot is a nautical mile per hour.
hour. Yes, of
So
course.
60 knots, therefore, is a nautical mile per minute. So if you know that 60 knots is 1 mile a minute, then 120 is 2 miles a minute, 180 is 3, 240 is 4, and so on. So you can very quickly estimate how fast you're going over the ground by rounding up or down to the nearest multiple of 60. So if we're doing 110 true airspeed, 100 knots ground speed, over the ground we are doing about 1.5 miles per minute.
Oh, good to know.
So
Thanks.
then divide speed, distance, time, you know, divide your distance by your speed, and you've got the time that it takes. So roughly 10 minutes. 15 divided by 1.5, roughly 10 minutes. So checks out about 8 or 9 minutes. That's the key to aviation, is all these wee silly rules that you'll pick up on how to make things quick and easy. So now what we can do is transfer that into the chart, or the plog, sorry. So we've got the ground speed in there, and we've got the heading. But notice that's true. Remember, we need to change that to magnetic, because magnetic's what we fly in the plane. Okay, so you can do it in the computer, but there's a reason I've not done it, and the reason I haven't done it is because it does it backwards, and I don't like it. By convention, west is entered as a minus and east is entered as a positive. In this computer, it's the opposite way around, so west is positive and east is negative. So you'd basically be teaching it wrong if you use the computer. Until you understand, I would recommend doing CDMVT. Okay, so if we just go CDMVT, you can draw all that out if you want, but you can also just go cadet. Compass to true, add east. Well, what is our variation? So if I come down here, can you see this line that runs diagonally across the chart? And it says 2.5 degrees west. I know when I zoom in I can't use the laser, which is really annoying. Can you see this line here?
Yep.
So
Yeah.
that is an isogonal. That is a line of magnetic variation. So everything along that line varies from magnetic north by 2.5 degrees west. So all we have to remember is compass to true, add east. So if we're going from true to compass, we add west. So that means magnetic heading is going to be 211. We'll just call it 2 degrees west. And that's the heading that we need to steer in the plane. And then we enter the time, 9 minutes. We always round the time up. So that's going to be 9 minutes. So now we know when we get to Errol, we're going to turn to 211. We're going to start our timer, and we know, or we're calculating that 9 minutes later we'll be over Balado. And we basically then just maintain, we check, we look out the window as we go. Does that make sense?
Yep,
Yeah.
sounds good.
Okay. If you're not sure, shout. Feel a wee bit of maybe apprehension. You're not screaming at me that you get it. Is there anything you're not quite sure of?
No, I
At
think
least,
it's okay. It just needs practice.
yeah, I was about
Okay.
to say the same thing. At least for me, like all of this makes sense. I just need to do it like 300,000 or 400,000 times, and
Yeah.
then I'll got it.
It looks like a whole lot of information, and it is, but basically we've measured 219 across the ground. That's our track. We're then taking the winds that are forecast, and we're calculating what heading. So if you were to think on that, you know, the wind, and this is why we draw the wind on, because the wind's coming from here. It's a crosswind. So it's going to be blowing us northwest. So we're going to have to decrease the heading slightly. we're going to have to reduce the heading so that we're pointing more to the southwest so that we follow this track line. That's all we're doing. We're doing trigonometry, but with a computer that's specifically set up to do it in terms of a flight plan. Okay, so who wants to have a go at leg number 2?
I
Sure.
think I got it. Oh.
Got it?
Go for it, Mal. I'll take the third one.
Gotcha. So what do you want first? The new heading?
We'll populate what you know. So go into go to the plan, press the plan button on the computer, and then you'll have it'll say leg 1 add, and then hit the orange button in the middle.
I'm already there.
Already ahead of me.
I was putting it in. So we got distance is 17. The true course is going to be 248.
Yep.
And that's because the wind speed is the same, wind direction is the same, variation is the same. The ground speed is going to be 114.38, and then magnetic heading will be 241, and track heading will be 239.
So the heading, the true heading, will be 239, and the ground speed will be 114.
Yeah, ground speed 114.
Okay, excellent.
Sweet.
That's what I got too. So now, what's the magnetic heading that we need to steer, taking into account the magnetic variation?
241.
Spot on. Cadet. Easy as that. And how long is it going to take us?
8 minutes and 55 seconds. So 9 minutes.
Excellent. Well done. It's as easy as that. You learn all that theory to basically fire all the numbers into a calculator and put in what it tells you. You're obviously using that knowledge to do an error check, but that's how, as a pilot, that's how you apply it. Whether it's an analog calculator, whether it's an E6B, or whether it's one of these newfangled electronic ones, or whether it's a VFR flight planning tool. That's all there is to it. So Martian, do you want to do the final leg from Stirling to Bailiston?
Yeah, I've already been working on it in the background. So distance 16 nautical miles. Course is 199. The true airspeed 110 knots. Wind direction 140, wind speed 19 knots. And that gives me a ground speed of 99 knots. And where are we? A time en route of 9 minutes 40 seconds. And the heading, that's what I need. Where is that? True heading, 190 degrees.
Excellent.
Correction angle -9.
So it's going to be 190 degrees true, 99 knots across the ground. And what's the magnetic heading that we're going to actually fly in the plane?
First, so 192.
Spot on, 192. And it'll take us 10 minutes. So that's it. That's flight planning. You pick where you want to go, and then you calculate the heading that you have to steer based on the winds and the ground speed, and therefore the time that it's going to take you to fly that leg. And if you do that for the whole flight, you then calculate how long the flight's going to take. You can then times that by 8 gallons per hour, and you can work out how much fuel you actually need. So in this instance, we need 14, but we've got 30 in the tank, so we've actually got a reserve of 16, which is enough for 2 hours flight, which means we've got more than enough to satisfy the final reserve minimums, but we've also got plenty to divert somewhere else if something happens at Glasgow. Okay. Does that sit better with you now that you've calculated a couple of legs each?
Just a few thousand more to go, but yeah, this feels good.
But you get what we're trying to do. You understand the sort of process of applying the winds to the track to get a heading and then converting that from true to magnetic.
Yeah.
And we're calculating the time. Okay, good. Now, I'm conscious we've been going for 2 hours. We've got maybe about 8 or 9, in fact, only about 6 or 7 more slides to go. And it's all on sort of correcting for errors in the air. Not at this point, it's not necessarily required. You've kind of got the basics of navigating and how we do it. Are you happy to continue on with those slides? It'll probably take us another half hour. Or do you want to leave it there? Is that too much mind frazzling for you this evening?
I mean, I could. I don't want to take up more of your time. I could totally do another half hour.
Don't worry about my time. It's no issue for me. I just don't want to bore you to death, and I don't want you to switch off because I'm giving you too much. So it's up to you guys. If you're happy to carry on, then I'm happy to as well.
Let's just do it.
Right, okay. I'm going to say at this point, take 5. I'm just going to get a coffee, and I'll be back at just before 10 past, and we'll
Okay,
get that.
I'll have to see if we are gonna make dinner at some point, but in that case,
Okay.
I'll let you know.
Okay, we'll try and make it as quick as we can. If you have to drop off, Martian, don't worry about it.
Yeah, Martian, if you have to drop off, like I can totally hold this over to the next time too. So if you're, I don't want to get between a man and his dinner.
Well, I think we're okay for now.
We'll come back in 5 minutes. Okay, we'll come back at sort of 9 minutes, 8, 9 minutes past, and we'll start again.
Roger
Okay.
that.
We'll see how we go on. Okay.
See you guys in 5.
Yo, I'm back. Who's here? No one with the sounds of it.
I'm here.
Oh, hello, Martian.
Hello.
How you find it so far? Is it quite a lot to take in?
Yeah, towards the end, yes, but it was fine. Need to practice the flight planning a bit, but
Yeah, that's the
it's
best
good.
way to learn it is plot a flight and go and fly it in the sim.
Yeah,
That's one of the great things about Microsoft Flight Simulator, with the scenery being so accurate, you can properly navigate this way. And it works how it works in real life.
yeah. Is this pilot logbook thing? Is there a template I can just find?
Yeah, I can send you over this one I've got. This one's actually a printed one. I just scanned a blank one. Um, you buy them online. It's just a plug, a VFR plug or a VFR pilot log.
As you will see, Martian, you won't really need to do the calculations later because Sky Demon does it all for you.
Yeah,
Yeah.
good
Sky
point.
Vector, sorry.
Good point.
But it's good to practice. So as
Yeah, I flew the first. I'd done 150 hours before I even downloaded Sky Demon. I wanted to make sure I had Dead Reckoning nailed, because you'd have to do it again in your commercials, so I didn't want to forget it. So it's good, it works. A testament to that. I've flown all over Scotland with Dead Reckoning. You just need to recognise its limitations, but it's also very satisfying to complete a flight if you've done it solely with Dead Reckoning, chart, pen and paper.
Yeah. Yeah, I've been messing around with the A320. It just does all the work for you. It's ridiculous.
Well, that's the reality. Even the G1000s, I think Tarek was saying the other day that the likes of technology and general aviation is more advanced than airliners nowadays in a lot of applications.
Okay.
The computing power that we've kind of unlocked in the past 20 years or so has really killed off a lot of these old techniques very, very quickly.
Yeah.
the techniques are still very much part of the syllabus for training, and until navigation becomes all but impossible with sort of computed systems, it's best to learn dead reckoning.
Yeah. One of the worrying things is the trend towards GPS, and quite a few unscrupulous nations have been shown to be messing with the
Oh yeah,
GPS signals.
absolutely.
So it's a great system, but I think there's become a bit of an over-reliance on GPS, so it's certainly good to know some old-fashioned techniques.
We do need to sort of start diversifying into inertial navigation systems.
Yeah.
So, I mean, like Airbus, Boeing, they all have it. They just mix it with GPS,
I
which
was
is
actually reading an article, can't remember where, but it was about, I think it was a flight where they flew to sort of Germany and they had a dog leg over the North Sea, and they actually lost. This was before they had GPS, and they were relying on VORs, and they would lose the signal in the UK for the VOR they were tracking outbound, but they wouldn't yet have the signal for the VOR they were tracking in Europe. And for 10-15 minutes, they would have to use dead reckoning to continue on track. This is a 737 flying a commercial flight only 15 years ago. Do you know what I mean? It's not so long ago we were actually navigating this way.
Aye, absolutely.
So, right, Null, I see you've unmuted. Is that you back?
I'm back.
Good. Right, let's get through this. So, how do we actually fly using dead reckoning? We've done all the planning. Here's a lovely picture of this very same chart. You can actually see the leg we were just using over here, but this was the first leg, way up the Great Glen from Glasgow to Inverness. And this is us in the cockpit of a nice old-fashioned Cessna 172. I think it's an M. In fact, no, it's an N, a November. That's what it is.
Correct,
So
it's an N.
this is as advanced as it gets, for me anyway. So what do? So on approach to the turning points that we've picked on the charts, okay, so this point here, this point here, this one here, we look at the chart and we familiarise ourselves with what we're going to see, what features are we going to see, okay? So when I get to this point here, which is my first turning point on this big long leg, I'm looking at the chart and I'm thinking, what am I going to see? Well, I'm going to be flying over a peninsula. I'm going to have, the mouth of a river. I'm going to have lochs. I'm going to have bays. Scotland's great for this kind of nav because there's so many obvious features even in the land itself. It's really easy to see the shape of these big peninsulas sticking out here. Okay, so I'm looking at the chart and I'm getting an understanding of that before we start the leg. Once I get to the turning point, once I determine that I'm overhead the turning point, I'll turn onto the heading, I'll start the timer, and then I'll populate my estimated time of arrival. Now, some people do all this on the ground, but the problem with that is if you do all your ETAs on the ground, you then have to manually correct those ETAs if your departure time was off. Say you get held for 5 or 10 minutes at the holding point waiting to take off. All of your ETAs will then be off. So what I was always taught to do is get to the waypoint, look at your watch, start the timer, and then add the leg onto, the time it's going to take you to fly the leg onto the current time and put that in your ETA, okay? It just means you're doing it as you go. Some minor mental math there. So right now, if I got overhead the first waypoint and it was going to take me 9 minutes, I'd look at my watch and say it's 17:14. So I'm going to get overhead the next waypoint at 17:23. We then fly that heading, okay? Remember, you've done a lot of work. You've calculated that heading. So you want to maintain it, okay? You don't want to start feature crawling. If you're using dead reckoning, you have to trust that that heading's going to get you roughly in the right place, okay? You want to continuously monitor your position, okay? Compare what you can see out the window with what you expect, but don't fly the chart. Don't start looking at the chart and go, oh, I can see a town down there. Adjust my heading 10 degrees, I'll fly towards it. Oh, wait a minute. That loch down there, I shouldn't be over that. I should be south of it. Adjust my heading left by 5 degrees. If you are not where you expect to be, use the features that you can see to estimate your position and make calculated corrections. Don't guess. If you're on a check ride or a skills test, as we call it in the UK, your examiner very well might ask you, if you tell them you're off course and you're correcting, they might ask you to tell them how you're correcting, how you've calculated your correction, okay? And we'll come into this, that's in the next few slides. Positively identify your next turning point by looking for obvious identifying features. And remember the considerations we made for the turning points and how we picked the points for the flight we've just planned. So we looked at Stirling. It's got a highway running north to south to the west of it. It's got a really windy river that runs right through the middle of it. It's got hills with a wind farm right in front of it. So as you're flying along, you're looking for these things. And you want to have at least 3 or so that positively identify what you can see, what you think is your turning point to be the turning point. Okay? And that's it.
Before you change slides, sorry, because I love this picture. And I want Null and Martian to think about this. Why is Andrew not flying straight up to his destination? Why is he going around on the left and then back across?
There's probably yeah, go.
No, you go. You go.
There's probably loads of mountains in the way and no good places to land.
Yeah, exactly. You got loads of high terrain, pretty hostile environment. Assuming it's clear weather, which in the picture looks it's almost clear. you could probably fly over those mountains, but if you have an engine failure, you're gonna probably land. You're gonna force land somewhere pretty inhospitable, and even if you do well in surviving the landing, then search and rescue has to come and find you. So
Yeah.
minor diversion
No,
in
good,
naval
really good
stuff too.
point that I've not actually touched on
Aye.
is the terrain over your flight.
I'm not having a go at you, Andrew. I mean, it's just a point, an interesting point to show because it's just we're covering so much today.
Yeah,
So
absolutely.
yeah, so I just wanted to point it out before you change slides because it's just such a wonderful picture for that.
So
Oh, sorry.
on you go now. On you go.
Okay, so presumably you would be making similar flights, right? Like I'm trying to think of a good way to say this. Like you'd be able to reuse this, right? With just correct, like redrawing it for the wind, probably, right?
Absolutely.
Okay.
I could take that track. Um, the headings, or sorry, the tracks and the distances are all the same.
Okay.
There is one thing that would change, and that is these key features that I've highlighted in red. If I go back here, you can see here, and I've not talked about these yet, but these key features I'm highlighting, you'll notice I've got a time next to them.
Oh, okay. I was
Um,
wondering because we were doing the time on this thing, like the first leg was 9 minutes and you had written 6 there, but it didn't look like it was the whole way, and I was like,
yeah, that's
okay.
that's it. So I'm highlighting key things that I'm expecting to see along the way that I'll check at that time. So I'm expecting to see, 6 minutes in. Obviously, this chart, the winds that I've used are slightly different from what I had on the day because this leg here is only taking 9 minutes, but on the day, this was 10 minutes at this point. But that's the only thing that would change. The rest of it's all, it's all fact, for want of a better term. The track across the ground and the distance isn't changing. So all you would need to do is recalculate the wind. The reality is, you do more, you just rub this out. You can just get acetone and rub this out
Gotcha.
on the chart. It's reusable. So you're not ruining the chart. It's designed to be written on and rubbed out and, sorry, erased, to use the American term, in case you're wondering what I'm trying to say. So yeah, no, absolutely no. Good question. You can reuse it. So on to the point then. You're not where you expect to be. So dead reckoning is a fairly accurate method of navigation, but it is inevitable that you won't be exactly where you wanted to be and you'll have to make some corrections. And there's a number of reasons for that. Can anybody think of any before I just give you them?
I mean, it's the lowest denominator, right? Like you can always do this, assuming you're flying VFR, right?
Yeah, you would normally do this VFR anyway. You wouldn't want to be doing this IFR. But what would mean that what factors might mean that you don't fly along the track that you should, even
I
though you've
mean,
calculated the heading?
wind might be different.
Absolutely. Biggest one, most obvious one. The wind's usually forecast over a large area. It's very generalized. The wind can be different in localized areas. So although the average wind might be 140 at 19, at Stirling it might be 135 at 22. And that
Cloud
will change your track. Okay. What else could you think?
cloud avoidance.
You might have to divert, absolutely. Um, Quite common to have to divert around something. So yeah, absolutely. But that's a conscious diversion. That's a conscious deviation from track. What might cause an unplanned deviation? It's okay. I'll give you. So the main ones would be winds, errors in your calculation. You fat fingered the calculator and you put the wrong winds in, or the wrong track, or you applied the wrong variation. You forgot to use cadet and you added west when you should have added east, or vice versa. Or you forgot to resynchronize your DI to the to the magnetic heading, to the compass. So although you're flying spot on the heading that you should be flying on a DI, you're actually flying the wrong heading because you've not resynchronized it, or you get distracted and you're not maintaining the heading and you start going off somewhere else. Okay, all of these things can and will happen to a certain extent on every flight. So the actual track that you fly is called the track made good. Very British sounding terminology there. TMG. It's probably called something else in America and Germany, but that's the terminology that I'll be using. And the difference between your flight planned track, FPT, and the track made good is known as a track error. So calculating the track error is the first part of correcting your course for most methods. However, if you only calculate the track error and then fix it there and then, you won't come back on course. You won't drift any further, but you'll still be flying off course. Okay. So we also have to get something called the closing angle. So we have to correct and stop the track error, and then we have to close back onto the track that we intend to be on. So there's quite a few ways to do this. I'm going to look at 3 ways to do this. You've got the 1 in 60 rule, you've got the standard closing angle rule, and you've got the inverse ratio rule. And I'm going to quickly give you some examples of each. Okay, this is where the animations come in. This is where it gets really exciting. So, what is the 1 in 60 rule? For every 60 miles travelled, 1 mile off track is equal to 1 degree off track. Okay, so if you're 1 degree off the planned track and you fly for 60 miles in a straight line, by the end of that 60 miles, you'll be 1 mile off where you should be. Now, how does that help you? Well, you can use some basic maths to equate this to any situation that you find yourself in. So let's come up with a made-up scenario. We're 10 miles in to a 30-mile leg, and we look out the window and we realise that we're not where we should be. So we measure it on the chart and we find out that we're 2 miles left of course. So how can we calculate this? Well, first of all, does everybody understand the position? We are here and we're supposed to be here. Okay, the black arrow is the track that we're supposed to be following. The dotted arrow is a track made good. So our aeroplane's here rather than here. And we've used a feature below us to identify on the chart. We've measured that distance to be 2 miles and we've measured that distance to be 10 miles. Is that clear? Because it's important that you understand before we go on with the problem.
Yes.
Yeah, that makes sense.
Good. So the total correction, as we discussed in the last slide, is the track error and the closing angle. So that's the total change in heading that we need to steer in order to correct our position and get to this point here. Okay. So the track error is 60 divided by the distance that we've gone multiplied by the distance that we are off course. That looks like a really confusing formula. How can I do that in my head? Well, the answer's quite easily because 60 is divisible by quite a lot of different numbers, 10, 20, 30, and you can usually very quickly round up or down to the nearest one of those numbers if you're not close. So in this instance, let's just do it how we would do it. The track error, to calculate our track error, we would do 60 divided by 10, which is 6, multiplied by 2, because we're 2 miles off course. That gives us 12 degrees. Okay. So we're 10 miles in, 60 divided by 10, 6. We're 2 miles off course, 6 times 2, 12. So if we were to turn right by 12 degrees, we won't drift off course any further, but we would then just continue to fly 2 miles off the course for the rest of the leg. And we would end up, rather than being overhead the town we were supposed to be at, we would be 2 miles north of it. Now that's just something you need to know. That's the formula. Once you've done it 1,000 times, you kind of remember it. 60 divided by the distance gone, multiplied by the distance off course. Does that make sense?
Yes.
Don't necessarily need to understand the mathematics of it. That's just the rule. So if we correct by 12 degrees, we're going to parallel. So what's the next part that we need to calculate? The final part of the problem.
Wouldn't it be we basically need to undo that and double it because we have 20 or we have 2/3 of the trip remaining. So it'd be something like 18 degrees of correction.
Look at you, now you're flying.
Yeah.
You're getting way ahead. So
Well,
what we would
I made
do,
a couple of dumb mistakes earlier. I gotta make up for it.
not at all. So what we can do is we can do a couple of things. So you've kind of skipped to the next part, which is really good. But if we were to use the 1 in 60 rule by the book, we would need to calculate the closing angle. And we would do that this time, not with the distance gone, but the distance remaining. So we've got 20 miles to go. So the closing angle is going to be 60 divided by the distance to go, multiplied by distance off course. So we're still 2 miles off course. So it's now just 60 divided by 20 times 2 again. So we would be 60 over 20 is 3, multiplied by 2, 6 degrees. Okay, and then if we combine them together, we need to correct our heading 18 degrees, left or right. Ooh. Got all the complex stuff falling at the easy one.
So are you going to turn 18 degrees to the left or to the right compared to the heading you were at before?
To the right.
Right.
Correct. We're left of course. So we knew that we were off course by 2 miles to the left. So we're going to turn 18 degrees to the right. Now that'll take us to, but we'll still be off course for the duration of the leg. But by the time we get to the end of the leg, we should be overhead again. So we've stopped the drift. We've stopped drifting off course by turning 12 degrees, and then we've added another 6 on to bring us back. Now what does that look like? So here's our wee plane. So for whatever reason, we've not flown along the track. Okay, the correction that we applied, our heading that we flew was not sufficient to counteract the wind. Okay, so over time we drift off course. So this is the eureka moment. This is when we realise we are not on course. So we do that quick calculation, and you can do that really quickly in your head. You then calculate I need to be 18 degrees more to the right. I need to steer 18 degrees more to the right to stop the drift and then get back to where I want to go. So we adjust our heading 18 degrees right, and then we fly that. Now that dog leg will have added some time, but at the short distances we are flying here at 30 miles, it's going to be minimal. It's going to be less than a minute of additional time. Okay, so we can still expect to be overhead our original destination at the same time as we calculated before. Does that make sense?
Yes, and the animation rules.
Wait till you see the next one. So the next one's called the inverse ratio rule. Now this is a very, very, very complex sounding thing for what is a very simple concept. So the inverse ratio rule just skips the step of calculating track error, and instead all you'd calculate is the closing angle and then multiply it based on the inverse ratio of your position in the track. Okay, so you just need to remember you're basically multiplying the closing angle by the denominator of the position. So if you're halfway along your track, you multiply closing angle by 2. And now this is what you just done in your head. So we were a third of the way along when we went off course. So all we had to do was calculate the closing angle and multiply it by 3, and that gave us our total correction. So we're skipping the step of calculating the track error. We're going straight to the closing angle, and then using that to calculate the total correction. So let's use the same example that we had before, okay? So 10 miles into a 30-mile leg and we're 2 miles off course. So what is our position along this leg at this point? How far into the leg are we?
A third.
Correct. So all we have to do is calculate the closing angle and multiply it by what?
3.
Correct. So for a third of the way, it's 3. If we're a quarter of the way, it's 4. If it's halfway, it's 2. And again, if you think about it, it makes sense because the further into the track you are, then the less you have to change. If you're really far off track really soon, you're going to have to change your heading much more than if you're slightly off track halfway in. Okay. So that should say CA times inverse ratio. I do apologise if I'm confusing you, but that should say closing angle. Okay. So closing angle is calculated using the 1 in 60 rule, just like we did before. But remember, it's the distance remaining. It's the closing angle, not the error. It's the angle to get back on track. So the closing angle, 60 divided by what?
20.
Multiplied by
3.
3?
Distance, of course, 2.
2. Excellent. So the closing angle is 60 divided by 20 multiplied by 2, which is 6 degrees. And then we just, we know we're a third way through the track. So then we just take the denominator, 3, and we multiply the closing angle by that. Okay. And that's 18 degrees. Same as what we calculated using the 1 in 60 rule. But this time we've only had to do the rule once rather than twice. So if you were in a position where you knew you were a third or a quarter or a half, this would be a quicker way to do it than doing the full 1 in 60. If you're not using halfway or quarter marks, then you would have to work out how far through are you. And if it's really obvious numbers like 10 and 30, you could do that, but it might not be apparent. So it depends how you've picked to mark your chart up, how you would do this. Okay, I don't always use halfway marks. I sometimes use 6-minute marks, and I'll explain that if we've got time at the end. But with a 6-minute mark, you don't always know exactly where you are in terms of the ratio, whether it's a half or a third or a quarter. It's just a position and a distance. So in those instances, the 1 in 60 rule slightly better. And once again, it's the exact same. That's the point where we went off course. We calculate the correction, and then we'll get to the point that we originally intended to get to at roughly the same time. Make sense?
Definitely.
I'm just going to add something because Andrew's done a fantastic job of explaining this. The main thing is to make your life a lot easier. If you plan on using the inverse ratio rule, have sort of along the leg, you have points where you're going to check to see your position, as Andrew's been showing you and explaining to you. So if you're going to use the inverse ratio rule, make sure that you know how far along the leg it is, what fraction along it is. So is it halfway through, a quarter way through, a third way through, a sixth of the way through, whichever it is, so that you can make that correction very easily and quickly. That's the whole point of this rule. So you don't have to go, okay, what's the distance I've traveled, and what's the full leg? Okay, let's divide and calculate that. You don't need to. You already know that it's a third of the way through, and then you only have one calculation to do, multiplied by the distance you already know, by that fraction. So it is very much about planning ahead of time, the inverse ratio rule.
Yep. And some people prefer to mark their charts with these points on track. Other people prefer other methods, just picking obvious things and writing the distance and the time next to it. Or, as I say, 6-minute rules, 6-minute markers, which is something that I was taught after I passed and started doing this and found them to be quite useful. But I use a mixture. I use a mixture of all of these depending on the leg, depending on what's available. And that's the whole point. If you understand this stuff, you can be flexible and you can use whatever technique suits any situation. Okay. So the final way I'm going to show you, and I think this is the end of the whole presentation. Save the best animation for last. This is a standard closing angle rule, so this is a wee bit different from the methods that I've just shown you. So for every 1 mile off course, flying the standard closing angle for 1 minute will bring you back on track. So you still have to calculate the track error to be determined using the 1 in 60 rule as before, but instead of calculating a specific closing angle, we're going to use a standard closing angle. Okay, now what does that mean? Well, it just means that there's for each airspeed, and again, if you're familiar, if you're flying a single type of aircraft, you'll know what it is. Okay, but in our theoretical aircraft, we're flying 110 knots. So if we fly a 33-degree intercept course or closing angle, it'll take us 1 minute for every mile we're off course to get back on that course. So don't worry, we'll do a worked example with this one as well. So after the correction time has elapsed, you're back on course. We can turn back on course, but we have to correct our original heading to ensure we don't get blown off course again, if that's what caused us to go off course. So we would have to apply the track error. And at this point, it's probably a good idea to use a different technique, but we can come on to that. So let's take an example. So 15 miles into a 40-mile leg, we find ourselves to be 3 miles off course. If we're travelling at 110 knots true airspeed, what is the required closing angle, total correction, and the duration? So let's do what we always do. Let's plot that out. Okay, 3 miles off course, 15 miles into a 40-mile leg. So the total correction is still track error plus closing angle. And the track error, can you see the pattern here, is still calculated using the 1 in 60 rule. So what's the track error in this instance? Who wants to go? Who wants to calculate it?
Is it 12?
Absolutely. So the track error is 12 degrees, purely by chance. I didn't actually mean to make the track error the same. So I don't know if you actually calculated that or you just had a lucky guess because that's what it's always been. But
I
I
just
did
guessed
mean to
12
change that.
every time.
So it's always 12. So the track error is 12 degrees, okay? So it's a different calculation. 60 or 15 goes into 60 4 times 3 is 12. It's just the way I picked the numbers, it ended up being the same. But once again, correcting for track error is only going to bring us parallel. So we need to now do the closing angle, and this is where it's different. Okay, so we know we're flying at 110 knots because we calculated the true airspeed on the ground as part of our flight plan. So we know that a 33-degree closing angle will get us back on course 1 minute per mile. Okay, there is a 2-minute closing angle in this table as well. And again, it depends on what you want to do. 1 minute's the standard that most people fly, I'm aware of. So that's it. Rather than having to calculate the closing angle, we just select it. We just memorize it. If our airplane does 110 knots true airspeed, then we know that the closing angle is 133. Okay. Now that should say 33 rather than 30. Now can you see that? So that's going to bring us back on course, whereas the other methods were bringing us to the end of the route, off track. But now we're going to come back on course and fly the original course. So the total, sorry, no,
Sorry, so we would fly that for 3 minutes?
absolutely.
Okay.
So the total correction, 12 plus 33 is 45 degrees. And we were 3 miles off course. So 3 times 1 is 3 minutes. So after 3 minutes, we would turn back to the original heading, but we would have to correct the heading so that we don't go off course again. Because for whatever reason, when we first flew the leg, we were off course. So if it was the wind that blew us off course, we would have to correct for that. If it was because of our error, we would have to figure out why. Did we just not steer the right heading? Was the DI not synchronized to the compass? Could be a whole host of reasons. If you don't know, you would have to do what we discussed the other night when we done the circuit training. You would have to pick a feature out the window and adjust your heading to track towards it. Because if you don't know why you went off, you don't really know your corrections. You just need to figure it out in the air using that turn time correct method. Okay. So what does that look like in the air? So here we are, we realise we're off course, okay? So we use the standard closing angle rule. We make quite a significant turn, 45 degrees, okay? And we start the timer and we fly that for 3 minutes. Once the 3 minutes is up, we're back on course. So we can't maintain this heading because we're going to then shoot past the course that we want to be on. So we then need to turn back towards the original heading, but correcting it for whatever error caused us to go off course. So we turn back, and in this case we're going to say it's the wind, so we've applied the track error to the heading, so we've added 12 degrees onto what our original heading was, assuming that the wind blew us off course, and then we'll fly the rest of the leg along that track. Does that make sense?
Yeah, it's
Do
good.
we
Yeah.
have an understanding?
Yeah, it's good. Also, I need to go in about 5 minutes.
Okay, we'll be done in 2.
Hmm.
So what might be a potential benefit of doing it this way over the other 2 methods?
You get
If you
back
just look,
faster. You get back
absolutely.
faster on track.
You get back on track, and why might that be an issue?
Maybe
Well,
it's like, oh, sorry, go.
you might avoid busting airspaces or hitting some obstacle you were tracking to avoid, you planning to avoid in the flight plan.
You've got it in 1. You might hit a giant pancake, or you might bust some airspace. Now you can do this with the 1 in 60 rule, but it requires a lot more calculation because you'd have to work out a closing angle in 5 miles. And then the maths would become a bit harder because you're not just working with small numbers, small divisors and multipliers, you'll be working with bigger divisors and multipliers. So you can still do this with the 1 in 60 rule, but you would have to then say, okay, I'm 15 miles off course, or sorry, I'm 15 miles in, I'm 3 miles off course. So that's 12 degrees track error. Now I want to get back on course, so I've got 5 miles to go, so I need to do 60 divided by 5. Okay, that's something like 12 times 3. And then that would multiply that by your, do your 12 times 3 and then add that on to your original 12. So you can see the math gets a wee bit more tricky if you get really short legs with the 1 in 60. But as with this, all we had to do was calculate the track error, turn right 45 degrees, time it 3 minutes, and then turn back on course. Okay? And that's really the main benefit of this. And you get back on course faster, so you don't need to worry because you'll be back on looking at the features. I was going to quickly run through this, but I'm conscious you need to go, Martian. I keep talking about 6-minute rules, and Tarek's already covered this. I use 6-minute marks. You can see one here. The reason that 6-minute marks are a thing is because you don't need to calculate your distance. All you need to do is divide your ground speed by 10 to know how far you've gone. Because remember, you do 6 minutes. If you're doing 60 knots, it's a mile a minute. So if you divide your speed, or basically if your speed in 6 minutes will be 1/10, because 6 minutes is a tenth of an hour. So you will go on 1/10 of your ground speed because your ground speed is in nautical miles per hour. So it just means that I can very quickly look at that. My ground speed, what was it? 100 knots, say. So 6 minutes in, I'll have gone 10 miles. So I can straight away start doing my 1 in 60 on this position without even having to measure the distance gone. I can just measure the offset or estimate the offset. Always figure out the width of your thumb, because you can very quickly, if you know you've got a 2 mile thumb, you can put that on the chart and you can go, right, I'm 2 miles off, I'm 1 mile off, whatever it may be. But with a 6 minute mark, you know you've gone a tenth of the ground speed in that time in terms of distance. Over here I've got a halfway mark just because it's suited. So I used a halfway mark. And over here I've got neither. I just used this because it was a really obvious big town, and I thought that was a good reference point, a good key feature. It just so happens to occur at 10 minutes. Best practice is write the time and the distance to these key features on the chart. I've only used the time. I probably should have put the distance anyway, but if you use 6 minute marks or multiples of 6 minutes, you can very quickly work out your distance anyway. And finally, after making your life so difficult, I have this stuffed in my kneeboard so that I don't have to do any mental maths. I use this table. This is what's in my kneeboard. So I just open the kneeboard up and I can go in. So if we look at the one we had, 10 miles in, and we're 2 miles off track, that's 12 degrees. Okay. We have 20 miles to go, 2 degrees off track, that's 6. 6 plus 12, 18 degrees. Total correction's 18. Bingo. If I was doing the inverse ratio rule, I would just go, I've got 20 miles to go, I'm 6 degrees off track, and I'm a third of the way through. 6 times 3 is 18. Bingo. If I was using the closing angle and I couldn't remember what the closing angle was, I just go in here, I go 33 degrees, work out my closing angle, and away you go. This is how I do it in real life, and I would encourage you to have something similar. But an understanding of the rules is still required, but it does save you doing all the calculations in your head and worrying that you've done it wrong, because you're probably already stressed because you think you're going to hit a mountain or something like that. Okay, any questions?
Yeah, could you please share that thing you put in the kneeboard? Because even I want it. It's amazing.
Yeah.
I've been trying to find the original file for ages, but I will get it over.
Also, are you comfortable sharing the presentation maybe?
Yeah,
Just
can do.
PDF or something. That would be awesome.
Yeah, no problem.
Thanks.
I have only this is a lot, and I'm sort of processing it. I have one question, but seriously, this is amazing. Thank you so much. This is bonkers.
No worries at all.
So what is the best way to practice this in the simulator? Would it just be like to get on? I mean, for me, I go on SkyVector, but like print off a map, calculate it all according to this lesson, and then like try to fly it. Will the simulator stack up to what the expectation is in real life?
Yeah, absolutely.
Sick.
When I was doing my PPL, I actually used the simulator to practice this. I would mark up my chart, I would fill out the plog, I would do all my calculations.
That's back in the P3D days. It's not
And
even...
that wasn't even MSFS, so you've got it even better now, because you can actually genuinely see out the window what you would see if you were flying. So the chart matches up. So
This is
yeah, I
great.
would recommend doing it in SkyVector. Do all the calculations through SkyVector so that it generates the plog and the charts for you. Print them off, or have them on a second monitor or something, and just fly it in the sim.
And
Great.
that's your homework for the next session,
Done.
which is to plan a flight something about, say, within a 30 to 50 mile nautical radius from your departure airport. Keep all these things in mind. Andrew hasn't covered all of the navigation, but he has covered a significant chunk. There's just so much theory when it comes to nav. So we will continue to cover things as we go along, but what Andrew's done basically some of the hardest stuff for you here.
Yeah, the first section is probably a standalone lesson, but we lumped it in together because we weren't sure that you guys both had that understanding of things like TAS and ground speed and wind vectors. That would be its own lesson.
Absolutely.
So we
It was
had
really
to kind of
helpful.
do both of them just to make sure that foundational understanding was there. Because the last thing we wanted was to jump in and start talking about true airspeeds, ground speeds, wind vectors, for you to go, what are these things? Well, trying to calculate them, you know, so.
Yeah.
Um,
So for next time, plan a flight.
I saw this wee image as well, and I just
I'll do my
stuck it
best.
at the end here. But this was something really interesting. It was actually posted on Reddit this morning, and somebody asked, these two flights both took off at the same time, and they're both going to the same place. They arrived an hour apart, almost exactly. Why? What happened? Any guesses?
The hint is on the picture below.
Picture below?
So this is a plot of the path the flight took.
Mountains.
Not quite.
Oh. Yeah, I guess that would.
Yeah, I mean, it's obvious they're taking a longer way, but yeah, I don't know why yet. Oh, it's shorter. Oh,
So they're actually going a shorter route than this flight here. But they take an hour longer. So
it's a long way. It could be the curvature of the Earth.
So the curvature of the Earth, this is pretty much a direct route here. So this
Okay.
is what the flight looks account for the curvature of the Earth. This is probably a Mercator map. So this is a longer route. The reason this took an hour longer was because the flight plans accounted for the optimum winds. So this was all headwind, whereas this was more tailwind if you flew
Oh.
north. But this pilot took off and the controller went, do you want to go direct to? And he saw on the navigational display, looked like a shorter route. Yes, please, I'll take that. But then he hit the winds. And in doing so, probably added a couple of tons of fuel burn onto the flight and took an extra hour as compared to the one that flew it as planned. So that just goes to show the importance of accounting for the winds and having a good tailwind, or at least minimising the headwind where possible. So just because it's a shorter route doesn't mean it's going to take you less time. It's all about ground speed, and the winds get a big say in that. But anyway, I
Right.
just thought that was quite interesting on the subject of navigation. I thought I'd chuck that in there for you.
Pretty cool.
Yeah, that was awesome. I need to run, but thank you so much. This was amazing.
No
And
problem.
I'll see if I can find